Hey everyone,
Hey
we're
there.
live.
Yeah, we have an amazing
Let's,
0 people watching.
yeah, 0 people watching. Maybe I should get onto the Twitters and link myself. Did I just retweet myself? Can I? I didn't know you could just retweet yourself.
Probably a new bug. It's like
Confirm.
whenever I open Twitter, it's just all Elon Musk these days. Like for the first, uh, it's like 20 pages.
Hmm. I I guess it's different for me because I'm following a bunch of like Japanese people, so the
Apparently,
vibe
they
is
fixed
quite
it.
different in Japan.
Elon Musk is having a bit of AI existential angst today. Well, 2 days
Hmm.
ago. Okay, so this time
Interesting.
around, it's slightly more.
Hmm.
Um, well, slightly more
Slightly
non-Elon
more what?
Musk stuff.
I see. You know, that's some of the problems with America, Twitter, and so many, so many like I don't know. I don't want to say like woke people, but there's like a lot of noise makers out there trying to make noise. Um, and yeah. But anyway, we're not going to talk about Twitter. We're going to talk about vector engine stuff once
Yeah,
people
so
kind of show up, I guess. I
apparently
have one.
there are 2 people here, like 2 people watching.
Yeah.
Say hello in the chat if you're there and watching. Got
That'd
five
be
people
really cool.
watching.
Oh,
Okay,
nice.
going up.
Yeah. So today we're going to be talking about this thing and getting things running on it. So this is one that I have that's a server one. So it's a passively cooled one that I had in my server, but I took it out. And now it sits where I'm doing experiments with you know hooking this up to like an external GPU thing and see if I can't get it running. There's a lot of work to do that, but um, yeah, it's fun, and I have a few lying around, so it's fun to try it. So I should go, I guess, into the history of this card a little bit for the people who don't know. Um, and essentially, this card is like the latest version of the what was called the Earth Simulator that NEC created back in, I think, like in the 90s or 80s or something like that. And yeah, the Earth Simulator was, just like it was the fastest supercomputer at the time, and that supercomputer used essentially the same architecture for its CPUs. And then there was like the Earth Simulator 2, and NEC was creating more supercomputer things, and they decided to try to address some of the issues that they had with like getting the software running on it, and the CPU is a special kind of CPU, so it's not ideal for running what they call like scalar workloads, like regular computations that like with small numbers, right? If you don't have a big vector, you can imagine the vector engine is not going to be very fast. So they tried to make a hybrid kind of Intel machine with vector engine accelerators. So even though this chip is totally capable of running a whole Unix operating system, um, it's just used as an accelerator in this latest generation, and we have been working with it for the last few years. We first started working on it when we were porting DL4J to it, and then we also made a plugin for Apache Spark to run on it, and that was, it works. And Apache Spark is not exactly the most vector friendly thing. There's a lot of overhead. So, when we got things running on it, it would run fast, but then getting the data to it and, kind of avoiding Spark and its slowness is the real key when trying to make this thing go fast. And yeah, so today we're going to try to get GPT running on this thing. Now, specs-wise, it's pretty interesting. It has more 64-bit floating point performance than a 4090, if I'm not mistaken, or at least a 3090. But it has kind of not so great floating point 32 performance. So essentially, when it comes to the consumer grade NVIDIA cards, their floating point 64 performance is like a 64th or a 16th of what you get from the 32-bit.
A lot.
Yeah, they cripple it a lot. And if you have a server grade like the A100 that we have, it's perfectly fine. You take this 32-bit performance, you divide it by 2, and that's pretty much what you get in the 64-bit performance. But this card only has like double the floating point 32 performance of the 64-bit. So it has like 3 point something teraflops, 3.7, I guess, teraflops of 64-bit floating point performance, and then 6 teraflops of 32-bit performance. But what it lacks in the in the upper body strength it has in legs, which is that it has 48 gigabytes of NVM, not NVMe, HBM2 memory, which is kind of cool, and it's really high bandwidth. So essentially, if you're able to kind of work within the last level cache of the thing, you're looking at a 3 terabyte per second kind of bandwidth between the core and the last level cache, 2 megabytes of cache. And Tesla's chips have 2 megabytes of cache per core, so it's like very similar. But then from the core to the memory, all together across all 8 cores, you get like 1.5 terabytes per second of bandwidth to the memory. So it has more memory than most GPUs, and is definitely more teraflops than most CPUs. And yeah, it's a card, so it's very interesting, particularly when it comes to the bandwidth. I think if it was possible to kind of come up with more bandwidth intensive deep learning tasks that kind of save on recalculating stuff, but in turn use more memory and then leverage the memory bandwidth better, you'd kind of find some AI things that work really well on this card. But right now, because everything is kind of made to run on GPUs, and GPUs don't have crazy bandwidth. I mean, they do have crazy bandwidth compared to a CPU. But the main thing is they have a lot of cores, right? So the floating point thing is their main strong point. So people will just use that as much as possible. So I don't know if this is going to be fast with what we're going to do today. But it'll be interesting to try it out and see what we run into, and just to show some of the people who are interested in the vector engine what it's like, and what it's like to program for it if you have all the SDKs and things like that. So what else did I want to say? We also have we also have in the game plan today to not just kind of get GPT running, but we also, maybe if we can get it running for inference, we want to try and experiment what it'll take to get it running for training. So we're going to try and get some very nano GPT kind of thing running on it for inference first. Then we're going to try to get training working on it. Yeah, that's what it's going to be like. Today is going to be a lot more technical and into the deep end than the usual stuff, but that's what it's like over in Express AI land. We do a lot of things.
So Freeman has just shared a link
Mm.
to a Tom's Hardware post from 2021, where CPUs can be faster than GPUs in some cases if they have AVX
Mm.
512
Mm.
with a 16-bit floating point. The interesting thing about the
I
vector
see.
engine is that it is kind of like AVX 16K.
Yeah,
So it can
it's
do
it's
very, very,
crazy.
very much.
Yeah,
Um,
it's like, yeah, that it's a whole complete order of magnitude more than that. But then the flip side of that is you need to have 16K things to I mean, just having 16K elements isn't really enough to get the full performance out of the vector engine, because it's made to be, like pipelined, right? Um, so if you're just dealing with 16K of data, you're gonna spend all the time loading the things, and then it's gonna do its calculation, um, and then it's gonna be copying everything out. And if that's all you have, then uh, most of the time is in memory kind of things and not so much in the thing. But if you have, like 10 megabytes worth of vectors and you're trying to calculate that, it's going to go through the whole thing 16K at a time. And it calculates, that 16K result in one cycle once you have everything pipelined, which is kind of crazy when you think about it. Um, and yeah, trying to cut like it becomes kind of a challenge to have enough data to actually move the thing. Actually, I think one thing that would be really good to show is the Wikichip um, thing for the vector engine. It is a picture that I look at often. So hopefully we don't get some terrible ads as we often do in Wikichip. But Wikichip has a section on the vector engine, and it has great images that kind of really go down into the details of what's going on. And I really like it and often refer to this when I'm programming the thing. Um, but essentially, the one of the first main difference, which is crazy, is that a GPU, what's the 4090 have like these days? Um,
oh,
it has
like
32,000 cores or something like that, or like CUDA cores, as they say. Um, but essentially, the thing has a ton of ALUs, which they call cores. But Intel also has a lot of ALUs, but they don't tell you the number of ALUs in their server. They tell you the number of physical processors that it exposes. Um, the vector engine has 8, and the next version of the vector engine has, I think, 16. It's double this. Um, but it's like fundamentally different. Where uh, with the Intel side of things, you're, you know, kind of packing 4 things together or 8 things together, and then doing an instruction on 8 things at a time. And then with GPU, uh, you're kind of making a ton of threads, and each thread is going to be working together. And it's kind of hard to explain, but in a GPU, you have a bunch of cores that are looking at the same instruction, right? So if you imagine you have like a bunch of ALUs that share a PC register, which is the current instruction that they're at. And then if you have like a branch uh, with a GPU, it will disable the outputs for the things that cover the untaken branch, and leave on the outputs of the things that have been taken. But then they kind of share that PC register. Um, in the vector engine, you have 8 cores, and what that means is that each core has a big vector processing unit, and the inside of one of the cores is something like this. So the main thing is there's the SPU, the scalar processing unit, and then the VPU. And the SPU is like a regular out of order, superscalar processor like you would get anywhere. but it is kind of clocked at 1.8 gigahertz, which isn't really fast these days. But the main, you're not looking for performance in the SPU. You're looking for performance by utilizing the VPU, and the VPU essentially has like these 32 what's called, what's the VPP stand for? I forget what it stands for, but there's 32 of those, and each one of those has like 3 or 4, yeah, I think 3 fused multiply adders, and then a bunch of ports for scheduling. So um, like the PlayStation 3 had no out of order. So when you're programming for an SPU, um, you kind of had to think about stalls and cycle times and all those things, because the hardware wasn't going to do it for you. But when you're programming on an Intel CPU, you don't really think about those things, because if one instruction takes more cycles than this one and they don't matter, it will reorder things for you to optimize that. The vector engine does this same optimization, and it even does it on the vector side of things. So that's like really, really cool. Um, and Yeah, you mainly get your performance by kind of using the SPU to get some numbers in place to point to a big large buffer of memory, and then you send that over to the VPU to process. And the way the VPU works is it kind of works on 256 values at once, and that's if you're doing 64-bit, and if it's 32-bit, then it'll be 512 things at once. And yeah, and essentially it will knock those things out, and then in a pipelined fashion. And when things are not ready, it will reschedule those things for you, and things like that. So it's a very complex machine, and because of that, it runs very hot. You know, um, and yeah, it's what I think is interesting about it is how similar this is to the Dojo architecture in various ways. Um, but what's interesting, I guess, about those ones is they have matrix multiply units, right? Systolic arrays for matrix multiplies. And that was kind of like a thing after the vector engine was designed. So the vector engine doesn't have a systolic array. Um, so it's going to be at a disadvantage there. And one of the other major disadvantages of the vector engine for deep learning in particular is that it has, so the VPU is limited to 32-bit or 64-bit. And when NEC was making and designing the chip, 64-bit processing was the main goal. Like that kind of 64-bit simulation of the entire Earth, down to the resolution that 64-bit can give you. That's what they wanted to do. So it's highly optimized for getting good throughput and enough compute to match the throughput for the 64-bit side of things. And then the problem is, for deep learning, it turns out you don't need precision, right? In fact, the less precision you have, it's like adding a new type of activation function, essentially, right? It gives you a new nonlinearity, which is a degree of freedom of your neural network when you have something that's lower um, kind of resolution. So the 16-bit floats and things like that. So the VPU is unable to do 16-bit floating point operations, and it can't do int8 integer operations either. It can only do 32-bit integers or floats and 64-bit integers and floats. And that's really the reason why you don't hear about it so much in in the news, because if it could do 16-bit floating point, and you're instead having like 1024, there is things you could do even without a systolic array that would get this to be, like it'd be 12 teraflops of FP16 if that was what it could do, which is reasonable, I think, pretty good. But it was designed in with a different mindset. And yeah, even I remember back in the early days of deep learning, we were always kind of wondering if uh, you know uh, like one thing that would happen often in the early days of deep learning is that you'd get gradient explosions all the time. And one of the tools that I remember reaching out to back in the early days was switching everything over to 64-bit to see if I can get it to train just a little bit longer. Like, yes, it was slower, but could I get it to a higher accuracy by going to 64-bit? And sometimes, yeah, that would help a little bit. But that wasn't, the answer wasn't 64-bit. The answer was going, having different things to keep the gradients from exploding and stuff like that.
An interesting
So
thing. So I've looked
yeah, go ahead.
into the link that Freeman shared, and well, it is essentially a C++ thing that's using OpenMP, and all it needs is a C++ 11 compliant compiler, and like maybe we could try that on the Vector Engine 2 later.
Okay. Can you send me a link? I can't I can only show it, but I can't click it.
Yeah, I'll send you the link to the actual repository.
Okay. Yeah. So then I guess like the last thing to really talk about when it comes to the vector engine is this part, right? Like this, the first version had 1.2 terabytes per second of bandwidth. The latest version that I'm running on the servers is 1.5, I think. And these are also a little bit faster. And this last level cache to core bandwidth is total 3 terabytes per second, which is quite amazing. And yeah, it's kind of a little overkill for 32-bit floats. It really works well if you're doing stuff with a bunch of 64-bit values and then kind of calculating and summarizing those into small numbers of 64-bit values and then writing them out, which is kind of the case when you're dealing with simulations. You kind of you're looking at the different, like every point kind of depends on its neighboring points. And then the larger you can make that area that you're searching, the better your simulation is going to be. So, I kind of, I've also thought a couple of times of, could we make like neural networks that are more hash table based, that require more memory, so to kind of skip on the computation and then make things a little bit more balanced. But yeah,
That kind
there's
of is what Slide appears to be doing.
Mm.
Yes, they are using
I think we never
a murmur
got
hash
into
and
it. Mhm.
stuff like that. So they are using a location-sensitive hashing function for some things.
Mhm.
So there may be something. I have no idea.
Yeah. I mean, I'm sure there's like that. I've never heard of these kind of things make significant improvements to the state of the art is the problem. Um, and so because of that, people don't really care about it so much. They kind of really care about when things really push the envelope of things. But like getting comparable performance on something else, it doesn't excite everyone, and so you barely hear about it. But it could be a thing. Um, yeah. So yeah, this is what it looks like. And then for those who missed it before, this is what it looks like in your hands, right? You got just a regular kind of PCI card and 300 watts of dual height. So it fits in servers and things like that. And I have 2 servers or 3 servers with these things in it. And we're going to use those today and see if we can't get this thing to chat with us. Like I think there's also some advantages to using this, right? Because like the um, memory is an important part of like GPT and those kind of things, right? And essentially, ChatGPT is good because it has so many parameters. And because this has 48 gigabytes of memory rather than like 16 or 32, that could be significant. That said, now NVIDIA packs 80 gigabytes of memory into their GPUs, so it's not going to be the unique advantage to this card per se, but you can get these cards quite easily and cheap these days, versus the H100s, which you can't get. You have to get in line, and it's going to take a while. So yeah, but anyway, yeah, this is what the old performance specs were. I think they do have 3.04, no, 3.06 teraflops of 64-bit is the latest version that I have. And this is what it looks like without, like, the naked card without anything in it. It's mostly memory and a little bit of processor, like that's the way it is. Yeah. And there is a 3.0 coming out, but I wish they did a little bit more, because essentially it's this essentially the same, double the bandwidth, so it has 3 teraflops of bandwidth, 16 cores, um, but that's not enough in my opinion, right? Like, as a person who is doing AI, it's not enough. It needs to have 2 of these in a single card, and that would
Yes,
be
Freeman is saying like
like useful.
there are newer cards,
Mm.
like the newer
Oh
vector
yeah, the new
engines.
one has 60. Yeah, that's the next one that's coming out soon.
The
So
but it's kind of
yeah,
I think it kind of came out, but unless you are building a supercomputer, you're not getting it because they have
yeah,
limited
exactly.
supply.
Yeah, yeah. But I think as a card, like for AI, right? The I think they were saying that they were able to get 50% more performance out of the new card. So if we do some back of the napkin math, the current card gets 6.14 teraflops, right, per single, through all 8. So if you got 50% more of that, then you would get 9 teraflops per card, which is kind of decent in FP32. But if you had 2 of those on a single card, you would get 18 teraflops, and I think that's kind of the baseline you would need to be competitive, right? That was my opinion, and I have shared that with some of the people that I know, and yeah, I think they should have also then added FP16 support, because if they did, then you're looking at a 40 teraflop card. And if they had also a systolic array accelerator for, you know, the simple matrix math operations, then you'd be looking at a 100 teraflop card, which is what the GPUs have essentially. So I don't know. Maybe they might not be done yet. So I think they might come out with a dual vector engine. So it'd have 32 total cores, which would be pretty good. Um, uh, oh, and another thing is that 6.14. That's like I think is that the 8 core or the 10 core? It might be the 10 core. So this would actually be 40 core card, could get 40 teraflops. So yeah, I think that would be a competitive card, but the market is it's very tough right now when it comes to AI cards and things like that. So it's going to be interesting to see what they do. Maybe we can come up with something that works better on the vector engine. That would be kind of cool.
I think looking into the slide stuff may be an interesting thing, just to see how it compares to CPU execution. But there's supposedly also like a G slide thing, which is, well, the paper isn't on arXiv, so it's kind of harder to look into it. But in the abstract, they claim to be even 16 times faster than that on a CPU.
That is interesting. Yeah, I might look into this if it's like we can see if it compiles first. That's the main thing.
Yeah.
Freeman has an interesting like for the matrix multiply. So that's also a really interesting thing. So the what was the size of it? Uh, the GPUs today have what's called those tensor cores, and those tensor cores are pretty small. Like as in they are very fast at doing matrix multiply, but the actual size, like how big of a matrix it's multiplying, is actually quite small. And so my idea, right, or what I was kind of arguing that they should do is to have a small matrix multiply systolic array on the card, like on the chip right next to the VPU. And if you had, you know, two matrices in the right format, then you could just put that, set the systolic array to start chomping on those numbers, and it would just do it. And while it was doing that, you could still do FPU operations or SPU operations. And it doesn't have to be super big. Like I think even having a 4x4 matrix multiply systolic array would could do significant speed up. Um, and I think what like the kind of trick that the TPUs and the GPUs do is that it's also not 32-bit. Like they're doing 16-bit uh, multiplies, and then only at the end do they kind of coerce that to 32-bit at the end of the thing. So in terms of chip real estate, you could actually make a small 16-bit only systolic array completely useless for the simulation, but just having that would make it it would give it a lot bigger and more interesting capabilities in the deep learning world, I think. And it's easy to take maybe like even a I think 8x8 or something like that systolic array would be pretty hefty. 16 by 16 would be super hefty, I think. But it's easy to take that and get 100 teraflops out of that. Much easier to do that than to kind of tune the FPU to get the same amount of performance. Yeah, so I actually think that they could keep the FPU, the VPU, as just being 32-bit or 64-bit only. But then just have a 16-bit capable or 16-bit only systolic array, and then that would make it, you could do 50 teraflops on the systolic array, and that would be enough to really balance the card in terms of the deep learning performance and make it really be like pretty even with the GPUs. But it takes years for the chips to come out, so if they were to do that now, we'd be looking at 200 teraflop cards by the time that comes out, I think. So, yeah. Although maybe I don't have any like insider information about the Vector Engine 3.0, so I can't be sure that it doesn't have a systolic array. Um, I didn't see any numbers that told me it did, so that's why I'm saying that. But anyway,
Okay.
so I think we can start going into step 2, which is looking at Pico GPT. So uh, the reason we are kind of looking into this is what was it? Karpathy came up with what was it? Min GPT, right? Yeah, I think that's what it's
Yeah.
called.
Min GPT and
So
Nano GPT.
and Nano GPT, and um, I was very interested. I was like looking into that because I kind of am interested in doing NLP on the vector engine because it does need more like memory bandwidth. It's more memory intensive in general. So I'm kind of interested in seeing how can the vector engine um, maybe be better for NLP um, than a GPU. I mean, in general, when you do deep learning on the vector engine, and there is a vector engine version of TensorFlow that NEC created that kind of works, it is significantly slower than a GPU, but it's not like half or like the CPU's here, right? And maybe like something takes 1 minute on a CPU, takes 5 seconds on a GPU. It would take like 15 or 20 seconds on a vector engine. So that's faster than 1 minute, right? But slower than 6 seconds, which would be 10x what a CPU can do. And that's like the typical performance that you get when you're using TensorFlow on the vector engine. Um, so it's significantly faster than a CPU, just not 10x. And if we're doing some kind of NLP thing that happens to leverage the bandwidth capabilities or the memory space of the vector engine better somehow, then it could get really close, I think, to the GPU performance compared to the CPU, because the CPU would still have slower memory bandwidth or less memory bandwidth, essentially. But anyway, so why am I interested in Pico GPT? So when I saw Karpathy's Min GPT, the first thing I thought is like, oh man, I should implement this in NumPy so that I could make it easy to port to the vector engine. And then this guy comes along and makes Pico GPT, which is a really quick and very simple NumPy only implementation of GPT-2, which is very cool. And just so happens that one of the libraries that NEC provides as part of the SDK is something called NLC, which is Numeric Library Collection, I think, is what NLC stands for. And they have this Python wrapper around it, which brings a NumPy API to it. And this is really cool. Plus, you can define C++ code to act as a kernel, right? I think they have it here in the just-in-time compilation. So you can create a C++ function and kind of set it as a custom library for NLC Pi, and then run it and get the results. So depending on how many NumPy things are not implemented in NLC Pi, we might do this. And I think it's interesting to also get into a little bit about what it's like to program C++ on this thing. So one of ExpressAI's things that we've been working on is something called Spark Cyclone, which is a Spark plugin to execute queries on the vector engine. And it's it works. It totally works. It works by taking the Scala code that you wrote, the Spark query, then we compile it into a C++ kernel just in time, and then we load that and execute it on the vector engine. And then we also cache it so that if you run the same query again, which is kind of the case for most Spark clusters, we don't spend the time generating the code and recompiling it. That part is quite slow, but if you're doing the same thing over and over, you can accelerate it with the vector engine. And we can look around what we can look at what it's like to program the vector engine, because it's very different from a GPU. So with a GPU, you have to make a function which has like implicit parameters of its location in the kernel, right? So you kind of have like a set of data, and then you're kind of breaking up the data into many chunks. Each core, each CUDA core is going to be looking at a different set of chunks. And the way you organize that is when you launch a kernel onto a GPU, it will kind of assign a number to each one of the cores in sequence, right? So that maybe the first one gets 1, and the second one gets 2, or maybe 10. The third one gets 20, and so on. And then you create a function that uses those indices that were pre-allocated into the core to find the chunk of memory you need to work on, and then you make a little program to work on that chunk. So you don't really write for loops, right? Like if you had a big thing and you wanted to kind of process it to calculate the average, you can't just write, a little for loop in C and get it accelerated on the GPU. You have to make a kernel function that is then kind of called on all the, in chunks of the element. So that means you got to change your code when working with a GPU. With the vector engine, you use for loops. Essentially. So if you have something like this, just a regular for loop, the compiler will look at that, break it into, it will generate instructions that break it into 256 byte, items, and then run the instruction to compile it. Right? You can do it explicitly by adding a pragma like this, like NEC Vector, which says that it should vectorize it. And it will complain if it can't. And yeah, and other than that, there's more things you can do to help it, like IVDEP, which means that hey, this might depend on other data, but you don't worry about it, right? Like now the compiler cannot guarantee that you're not overwriting data with what you're doing. But by putting IVDEP, you say, I guarantee that this data is not going to overlap, so you don't need to worry about that. And the reason why you have to worry about that in here is because the instructions that you're writing, like this for loop becomes a single instruction type of deal. So let's say the count was 100. What this would do is do what is it? So it would do a Boolean kind of operation on all the data up to 0 to 100. One instruction would calculate these zeros and ones, and then we would do another 100 ands, right? So take this vector with a bunch of zeros and ones and the output and it together, right? So that's the interesting thing about how that works. And when you're using the NEC compilers, you essentially write regular for loops, but then you add these like pragmas to it to kind of control how it's doing things. Now, an important thing to keep in mind is that this is still just one core, right? There's 8 cores in the vector engine, and if you want to utilize all of them, you have to use multi-threading, right? And you can use OpenMP to do that. So it's possible to mix both OpenMP and vectorization in this. So if you have 2 loops, one is something that just breaks up the array into 8 pieces and then starts processing each piece in a for loop. Then inside, you just have a regular for loop, but then it gets vectorized so that it works on 256 or 512 items at a time, depending on the size of the thing. But what that does mean is that you're kind of limited to what you can do inside of a for loop, right? So, you can do things like you can put multiple instructions inside of a for loop, and essentially the compiler will split it into multiple for loops for you and then change each one of those into an instruction. But if you did something like call a function inside of a for loop, that's going to cause problems. And having complicated if statements inside of for loops, simple ones are supported, right? So like this, something is less than some other thing set. There's an instruction for that. But if you have a very complicated for loop inside it, or a very complicated if statement inside of a for loop, then there's no single instruction to support those things. So you don't get a vectorized loop. You just get a regular loop that would be run on the SPU side. And when you're running things on the SPU side, you're not really getting the performance that you kind of expect. So it's really important to kind of keep things simple and look at the output that you get from the compiler to make sure that you're vectorizing all the loops that you can. And that can be very important. You also want to make sure it doesn't over vector things, right? You don't want to vectorize the wrong loop, right? Like that's not the one you need to vectorize, it's the other one. So sometimes you have to tell it like no vector to say, don't vectorize this loop, vectorize the other one. But other than that, it's like regular C++. And as long as it can inline, like it will aggressively inline all functions in C++. And as long as it can simplify those into instructions, vectors instructions, it will compile it that way. But that's the NEC compiler. And there's also Clang available. And with Clang, you're kind of stuck with, doing things on your own. It's not gonna, or I don't think the latest one can auto-vectorize loops. I could be wrong. I haven't checked out the Clang ones in a long time. But when you are dealing with Clang, and one thing that we can show is the TFVE. I guess tensor.
It's a VETF, I think.
Yeah, VETF. So in SXOR dev, there is the TensorFlow library. Like VML. And in here, yeah, but I mean, it has both. So in here, it's using both the NEC compiler for these files, but inside of the intrinsic folder, they're using Clang for these files. So if you look at something like argmax in here, you can see it's mostly standard C++, right, or C, with for loops. And you'll get these NEC pragmas for things like this is a good example of don't vectorize this one, but vectorize that one, and stuff like that. But then the intrinsic versions, if you look at what these look like, you don't have pragmas, but instead you see something like VBRDD VSL and VLD VSSL. So this is vector load, and this is vector floating point add, right? And things like that. So you can kind of do assembly. You have to program in an assembly like fashion when using Clang, which can be very fast, and that's why they use it here, right? They can't get the NEC compiler to generate exactly the code that they need, so they have these things which use these pragmas to implement something that looks a lot more like what you would expect like AVX 512 to look like, or AVX2, right? That stuff kind of looks like it has these like unrolled loops and things like that. But this is kind of interesting how you get like these sums of the first 256 versions of that, and then you load those things, and then you add them, and it's like unrolling the loops in for, which happens to be slightly better than doing it the way that the NEC version does, I think. Probably a pipelining thing where they've like gone down, they've profiled it, they've seen that there's some stalling going on, and they could get more performance because they have enough like they have enough registers. So that's another thing. It has a lot of registers, a lot of vector registers too, and making sure you're getting the most out of those registers is something that's sometimes difficult for the compiler to do, because it's inlined all the stuff, and so it has a lot of things that's allocated to registers, and sometimes it's like, yeah, I can't inline anymore. We got to reuse the register, so it gives up. But if you're explicit like this, you can kind of fine tune the register allocation, and Yeah, because the registers are big, it is important to kind of keep in mind the register pressure you have, because if you have a bunch of functions that get called, yeah, saving those registers can be pretty heavy when they're vector.
Yeah, so Freeman brings up that, well, previous versions kind of didn't have visible intrinsics or inline assembly. And if I
Yeah,
remember correctly, it's also not like exactly trivial to get intrinsics in the regular NCC.
yeah,
But the Clang
it's
stuff
essentially
is
impossible.
different.
Yeah. So when using NCC, you can do assembly with a regular assembly block. So I have done it. But when I have done it, that can very often kill performance because the compiler kind of throws up its hands when you do that. It's like, oh, I don't know what this is doing. It can no longer inline stuff, and it can sometimes really tank performance. So you're kind of stuck, writing a lot more in assembly than you might want to when doing it. But it is possible, and I have written assembly blocks in that to test things out, and it works. And you might be wondering, well, what does the assembly look like? Well, luckily, you can go to nec.hpc, which is a fun, or hpc.nec, which is a fun top-level domain that they have. And in the documentation, you can see the SX Aurora Vector Engine Assembly Language Reference Manual and the Instruction Set Architecture Guide. And I download these like all the time. The ISA guide is really what you want. And it kind of goes into details about how what instructions there are and what their kind of pseudo C code would be. And essentially, when using the NEC compiler, you can, um, kind of assume that if you write a loop that is vaguely like this, then the compiler will get it. Um, So for example, one example, which is a really good one, a good example of one of the instructions is vector floating compare and select maximum or minimum. So if you think about what that's doing, right, it's like you're comparing an entire vector of things and then picking the max thing out of that. So if you're writing that in C, you would have like a for loop, and then you'd have your max that you initialize to something, and then you go through and then you have an if statement, and if that is bigger than the other thing, or if that is less than the other thing, then you set it, and then you go. So if you think about what the assembly language would be in an Intel CPU, you have a branch, and then you have a compare, and then you have a branch, and then you have a store, then you have a jump, right? So it's like kind of doing this, kind of loop kind of thing in the assembly. But in the vector engine, it's one command: VFCM, VSSL. Here's the registers, and then you get a scalar out of what the largest number was. And this was important for us when using this to figure out like the max when we were doing a big, what was it? What were we doing before that we needed to get the max stuff?
We were doing like a top
argmax.
K type search.
Yeah, top
So
K thing.
yeah, argmax.
Yeah. So this is not really C, and it can be a little hard to understand, but once you get it, it's not too bad. But essentially, VM is what they refer to as the vector mask register. So your register can be masked, or your array. So you can, for example, have an array of 1 to 100, and then let's say you only want to get the max odd result. So you can, if that, like, you can run something that masks all the even numbers. So the vector mask register will have zeros for the evens and ones for the odds. And it will apply that mask and only take into account the things where the mask is one. So that's where this thing comes from. So when you see this, you're like, okay, so you can use the vector mask register, and then if it's the max, then that's what it's going to set the thing to. And you don't have to write it this complicated, but essentially you can write for. Um, I guess you don't even have to write this inside, but if you set something to the first value and then you have an if statement where it says if it's greater than temp, then set it. It will notice that that's a max min pattern. It will tell you in the compiler output and then generate the code. So it's a um, pretty amazing what it's able to do when it works. And when it doesn't work, it's very frustrating. But it is pretty good. And yeah, and the
So
VE
for
has an amazing shuffle instruction. So it has a couple of complex operations like compress. Um, what was it, like vector compress? What was it called?
there's gather and scatter, and
Oh
then
yeah,
there's
gather and
also the
scatter.
compress stuff.
Yeah, here's the shuffle. Um, yeah, and the compress is it will take all the zeros and get rid of them, right? So you have like a single instruction that goes through and checks whether the thing is zero or not, and kind of shoves it to the beginning of the loop. And you can think of when you're programming that in regular C, how much code you kind of have to do to represent that, um, to do this kind of thing. And not only can it do this, but it can also do expand, and it can also shuffle in various random directions. Um, and that's really cool that it can do that. But the thing to keep in mind is it's not necessarily all that fast. And the reason for that is you have to go back to the Wikichip vector engine things. Um, so in here, you can see that there's a store and a complex port. Then there's 2 ALU ports and then 3 FMA ports. And things like vector shuffle and compress and max and those kind of things are actually complex operations. So there's only one of those. And because of that, it can't really pipeline those as much as you might expect. But if you are using that as the last step in a big process, right? So you have a bunch of multiplies and adds and maybe some masking, and then you compress the final thing and then store it. Then it can be quite fast. But it's something to be careful about. You can't just shuffle willy-nilly and kind of expect that it's going to do it at a super fast speed. There's only one of them, and it's it can be a source of contention. You also it's shared with the storing, so that's another thing. So you kind of have to have enough free registers to get the maximum performance, and most people don't think in those terms, right? Like, yeah. Oh, I think more important is this, right? Like, so there's these 32 VPPs, right? And then port 0 is this complex operation. So there is this complex. I think that's a separate kind of complex, but the idea here, like the important idea to take away, is that um, the vector engine is fast because of these 32, like, you know, essentially AVX kind of things that it has. So it's going to take a bunch of things and calculate them all at once. 32 times 3 FMAs is a lot of FMAs and ALUs, but there's only one complex operation port, and it's very complex. But that's what's doing shuffle, that's what's doing compress, and so the speed that is going to do that is faster than this, faster than the SPU, but not as fast as this would be. So that's an interesting thing to keep in mind. And I think for a lookup, there's probably a lookup one. I mean, it's always like yeah, like getting the thing of uh, of I, right? Like that lookup thing, there is an instruction for that, if I'm not mistaken, an explicit instruction for it. So if you write it down, and use the NCC compiler, it will tell you that it's discovered that and do that. So that one is one case that is actually included. Vector floating, iteration, add, and multiply. So these get really complicated. But that's the kind of fun thing, is getting the compiler to say, "Hey, I've generated this instruction for you," and then that's very cool when that happens. And you don't have to compile you don't have to write assembly for it. You're just doing the C code. And in general, Freeman has an interesting thing, which is about the vector length. When doing C code, you're almost never cognizant of the vector length. Like in general, you don't necessarily want to chunk things in 256 or 512 or anything like that. You just do it on the array and let the compiler kind of chunk it to 256 for you. I have done like manual 256 chunking. And depending on what you want to do, yeah, it can be really fast. But in general, you don't like it's kind of hard to beat the compiler when when doing this thing, right? Yeah, like I've totally done it where I've like, explicitly put 256, do this, don't vectorize that, vectorize this thing, which is and I set the explicit vector length, which you can do with a pragma to 256. And then I have an if case for when it's less than 256. And then I tell it to vectorize that, but with a small vector. And yeah, you can do that. And there's pragmas to control it so that you can do it yourself. But yeah, sometimes you'll find it's hard to beat the compiler. It doesn't always go faster. Like, now it's 2 times slower. Damn it. That happens all the time. It's like I should have just used the regular code, and that would work. Okay. So where were we at in the
Yeah, we wanted
yeah,
to
Pico GPT. Okay, so
preview
let's
Pico GPT
mhm.
and come up with a game plan.
Yeah. So so essentially I have Pico GPT running here. Okay. So if I run something like this, let's give Intel all the cores that it needs. So there's this GPT-2 Pi file here, and then a GPT-2 Pico, which is smaller, but I think it does more or less the same thing. So I think, NumPy, everything's implemented in NumPy. There's no other imports, which is absolutely amazing. Like, that's so amazing that somebody would do this. And we have NLCPy, which is NumPy for the vector engine. So step one will be to change this, get it running on the vector engine, and see what breaks. And then whatever breaks, we're going to implement it either in Python or in C++, depending on how crazy of a thing it is. And yeah, we're going to give that a shot. You can see here it takes about 21 seconds to run on the CPU. This server that I have has 48 cores, or 48 threads, 24 cores, dual socket Intel machine. So it's no slouch.
But if you want
But
to
let's see
give
if
it its fair chance, let's limit it to 1 CPU and 12 threads.
yeah.
And I've tried,
so
while you were talking, I've tried out the OMP procbind environment variable, which is supposed to make it stay on 1 CPU, but apparently it doesn't do anything at all. So instead, you can use task set -c 0 to 11 before the Python command, and then it will use cores 0 to 11. No, it's actually a process call that you
command.
do. So yeah, it's command.
Okay. See, so task set C.
Yeah, minus C and 0 to 11. So 0 dash
0.
11.
Oh, dash 11. I see.
Yeah,
So set it to cores 0 to 11.
exactly. And there should be
And
a space
why?
between the C and the 0.
Okay. So if we run it this way, slightly faster.
Yeah, 7
7. So
seconds.
20 to 7. That's much faster. Okay, so that's the time to beat, I guess. 7 seconds. Um, so let's see. So anyway, okay, so I'm in virtual env in here. Let's give ourselves a little more.
Oh, one more thing before we kind of get
Hmm,
started properly. I've noticed we are still in the talk shows and podcasts category on Twitch.
Oh,
Maybe we want to change that to the programming category.
how do I do that?
I should be able to log in into the creator portal and do that.
Okay, let me give that a shot. I can remember. Gotta do it on the browser that's logged in.
Yeah.
Okay, so inception stuff here. Let's go to the channel. Is it the channel? Oh God, I can hear myself.
You should probably put
Uh,
put it in mute or something.
yeah. Okay, username, channel, and videos. Do you know where it is in the settings?
Not exactly, no.
Video producer, broadcasting. Can add it to a collection. Settings, stream, exclude categories. I have no idea how to
So in
do that.
principle, you should, like I'm looking at the documentation here. So
Hmm,
you go to the creator dashboard, then to stream manager,
Yeah,
then edit
yeah.
stream info, and
Edit
then you can
stream
under
manage.
category select.
Edit, edit stream info category. Aha, so I can do code or no, programming.
Yeah, it's game development and software something, I think.
Software and game development. Okay,
Yeah, and it has changed.
so
Cool.
that's good. Hopefully, I guess some people might have been thinking that we're going to get some, simple AI talk show, and they're getting way into the weeds. I can imagine how crazy that is.
Yeah, I mean, yeah, it's going to be like way into the weeds.
Yeah, this is quite high level discussion on AI topics, I would say, or low level discussion. Um,
Yeah.
okay, but anyway, so here we are. Uh, Ideally, you can pip install NLC Pi to get the wheel installed, and it doesn't include NLC. So you do need to get NLC from an NLC license. And anybody who has gotten their vector engines by not so official means can feel free to talk to me about it. Can't do anything for free, but I can acquire licenses legitimately, and we can work things out, I think, in a way to get people to have it if they're interested in playing around with the vector engine, but using the like official NEC compilers instead of the open source stuff. Okay, so anyway, so we have NLC Pi, and
Now
if
you need
things
to
are
make a what's the name? You need to enable the NLC environment. I always forget how
yes,
exactly that worked.
so to enable the NLC environment, you source opt NEC VE NLC, and then you have your NLC version bin, and then you put NLC vars.sh or CSH, depending on how long your Unix beard is. And yeah, you source that, and then that puts a few variables into your environment that gives it the paths to
I'll
things.
be
Pretty
back in a
simple.
second.
Okay. So okay, so we have that, and then if I haven't messed up anything, we should be able to run Python. This is the same thing, so I will get rid of this task set. Let's run it and see what happens or what breaks. But it might be a little difficult to see, is it using the vector engine or not? So we can bring up a terminal and look at another thing. Let me see if I can get out of this, this mode so I can have a window. Okay, so that was interesting. Let's try that again. So I can log into my machine, then we can do opt NEC VE bin, and there's various Unix tools in the VE bin folder, like strace and time and top and things like that. So I'm going to run top, which should give us a view of stuff, view of the VEs. You can see it says the default VE node 0 is offline. I have a few VEs on this machine. To see what you have, you can do VE command info. If you do that, not found VE monitor. Are my VEs down? They could be down, which is interesting if they are. Let me check. So VE node number is how you set the vector engine that you want to work with. And then we can do NEC VE bin top to get that, but the VE was a VE node number. There we go. Yeah, so we can see there's one VE thing running here, and I think one is empty, 2 is running, and 3 is also, yeah, so I have 3 vector engines in this machine.
Right, the machine has this interesting situation where there is no node number 0 or something like that.
Yes. Yeah, and I know what to do, but I'm too lazy to do it. So there's a way to renumber your vector engines. So you have to go in and you have to delete the node configuration mapping and then rerun it. But I'm kind of too lazy to do that. For some reason, I cannot run VE command info.
Yeah, that requires the MPI stuff to be running.
Interesting.
And yeah, I'm not
Did I
entirely sure
break the
why it
MPI
isn't
stuff?
on that machine, but it, in principle, it should be working with the NLC Pi stuff, because I think it doesn't require the MPI stuff anyway.
Yeah, the MPI stuff, the MPI support is an optional thing that I didn't want to pay for because I don't have InfiniBand on the server, so it doesn't have it. But the MPI system should be running. But regardless, we don't we can see from top that one is empty. Opt NEC VE bin top. We do VE node number equals 1. Okay, so we can see
Is
one doesn't have
the node
anything.
number 1 the older one?
That's what I wanted to find out with VE command info, but we'll try both and see. So we're running that. Don't see anything being run.
Is
That's a
the just as a sanity check, is the file that you're working on actually updated on the server? Because as far as I can tell, it isn't.
It is not. Yes. So I have set this to automatically upload, but I guess it is not. So
It still
let's
isn't.
click right here, upload files. Yes, upload that. GPT-2.py. Are we running GPT-2? Hold on. Save this, please, and then upload it. Why is it not uploading? It is not identical to the remote one. Oh man. Hold on, let me go to the old UI since I might, that one's a little bit easier to work with.
Yeah, I really don't know why you change to the new UI. I really don't like it.
I don't hate it too much. But it's definitely missing features that I enjoy. So I'm a guy who has the project and structure on the left. Um, and I really like to be able to kind of have an alphabetical list of the functions so I can skip around the file very, very quickly. And unfortunately, yeah, that doesn't always work. Anyway, so let me bring up the deployment tool, browse the remote host, make sure that the configuration is set correctly. I think we want to make sure that it doesn't also deploy the models folder because we already have it. We don't need it. I'll add local path models. Just make sure that that is not deployed. Okay, and whatever, I'll just do it also. We can totally
The
like
difference is
edit
that
directly.
you changed the GPT-2 Pico file locally.
Oh, I did?
Yeah.
That's what it was. I'm an idiot. Okay. Of course, the problem exists between chair and keyboard. Okay, so this should be NLCPy as NLMP. And now we can try it, I think. So saving should update automatically. I can check to make sure. I can just refresh. Yeah, okay, so now things are correct. We're on the correct file. And I'm in the correct place. And now if I do VE node number 1 based on GPT-2 we can see that I'm running the wrong version of Python. So if I activate that, it will
and now you
say,
need to enable the NLC.
oh, I forgot this.
Thanks.
Okay, so let's source the NLC bars. Okay. And now let's do that. And it is running.
It
Good
is
job,
running,
NEC.
but
It is
it
so,
is
it's
very
running
slow.
very slowly, but it is running. So I guess we should also check the top to just verify if we're running properly. Okay, so we are running properly, and we can kind of see the threads. Unfortunately, when using AVEO run, which is their vector engine offloading library, it's always going to say the CPU is 100% because it is essentially like just in a busy loop waiting for commands. And so whenever it's not executing something, it's going to be in that busy loop waiting for commands so that it can execute as fast as possible. And the side effect is that the CPU is always at 100%. So it's not very useful. But it's amazing that just worked. That is so cool. Because this hasn't been the case for a lot of things.
Well, I wouldn't.
Anyway,
I
so
mean,
let's.
just works isn't quite the right thing to say here, because that is,
It's incredibly slow.
well, really slow. Yeah.
Yeah. So let's also run it on BE3 to see if there's any regular performance difference.
I can give it
But
the
we
last
should
6 seconds to
profile it.
finish.
Yeah. So it's correct, which is good. Let's also run it on 3 to see if that makes any difference. I do think 1 is the old one, and then 3 is the Vector Engine 2.0. But there isn't that big of a difference between the two, so I don't expect a big difference in performance. That one took 1 minute and 47 seconds. And this one seems to predict about 1 minute or so.
Yeah, I guess
That's
so.
pretty significant if it's like 1 versus 2. Okay, so there comes a point in every GPU programmer's life, quite often, when they implement their algorithm on the GPU and it's slower than the CPU, and they don't get it. It's essentially a given, right? Like, it doesn't like I don't think any time when we were implementing like GPU kernels in DL4J that we ever had it just be like, oh, it's super fast now. We're done, right? Like that's never happened, right?
That's true.
It'd always be like, okay, it's very, very slow. Now we got to figure out why it's slow and then optimize that, things like that. Much easier to do in C++ than to do when working with NumPy. Um, but yeah, we got to go see what's happening here if there isn't
So
a way to update
Freeman
it.
guesses that we are PCI bandwidth constrained, because
Um,
it has like its batch size is 1, so
hmm,
we're paying a
that's
lot
a good
of communication overhead.
yeah, that's a good point. There is so the way to really test that is to try to do multiple batches or multiple things, one after another, to see if loading the weights onto the PCI bus is the majority of the first time, so that if we time the second one is that much faster than the first. So I think we have main and prompt. Now, if we do this like twice, well, let's see, what is we're loading, then encoding the prompt. So let's do this in a for loop. So for prompt in prompts, right? We'll do this. And then the output text, let's make that just text over here. And then we're going to return it at the end of the loop. But instead of just setting it here, we'll do append, or I guess plus. Let's add a new line, I guess, or something like that. Okay, and then we specify prompts as a list of str. Okay, so if we do this, then the loading will happen separately from the prompts. And then what we have here, so let's do this same prompt, but multiple times. 2, 3, 4, 5, 6, 7, 8, right? And then we'll encode each one, generate, decode, and append to the thing. And then we just fire main. Seems reasonable to me.
Okay, let's see.
Yep. Type is not subscriptable. We are not in a good language. We're going to use primitive types. Okay, let me go back to the presentation mode, but not in full screen. Thank you. Okay, so unfortunately, I think so we're stuck with fire and the way it works. So I think what we'll do instead is we'll get prompts, which is a str, and then we'll split it by commas.
Yeah, if you give me about 40 seconds more, I'll also have a profiler output on our original run.
Oh, okay. Oops, I think that's doing stuff.
Yeah, I'm also using VE Node 3 for this.
Oh, okay.
That's what I'm saying. Give me... now it's about 30 seconds more. Because,
1, 2, 3, 4,
knowing what
5,
is taking
6,
the
7,
most
8.
time is probably going to be more useful than guessing.
Yeah. Are you using which VE Node number are you using?
I'm using 3 at the moment because that's the fastest one. 2 is being used by a server, and yeah.
Yes.
Interesting.
You're using V2 for Vecto, our incredible vector database. And if you want to learn more about Vecto, you can email us at sales@express.ai.
Or you can try to decipher the sales copy on Vector.ai.
Yes. or you can peruse our incredibly bad sales copy, which we can assure you is not produced by an AI, because if it would be much better if it was.
Okay.
So,
I should have told
okay,
it to...
you're done. So let me...
yeah, I'm done. I should have told it to
run
sort
this
it by time or anything.
Did you use ftrace or something else?
I used Python's C profile.
Oh.
And yeah, if you don't tell it to sort
that.
on anything, the output is kind of hard to really use.
So I have some ideas of things that could be slow, like GLU, because this is implemented in Python, essentially. So we are launching one kernel for this.
So apparently
Yeah,
we are
one
spending
kernel.
55 seconds in the attention
Mm.
function, 58
Oh,
seconds in the MHA function. GLU is actually apparently kind of fast.
okay.
It's at the moment we are apparently spending
Softmax.
most of the time on attention.
Mm. It is the softmax, so that kind of makes sense. Is this softmax from NumPy? I don't think so, right?
Now the softmax is
Okay.
supposedly takes only 1 second total. Like for
Ah,
all it's 5,000 calls. But we
mm.
are kind of spending a cumulative time of 55 seconds in the attention function.
So either in the matrix multiply or the square root. Now this should be quick. Has to be quick. Like maybe the transpose. That should be fast too.
Yeah, let me ask it to sort on something useful so I don't have to
hmm.
scroll up and down.
Maybe I should break this down so that we have so query key. So we'll take Q and T, and then it returns Q at keys transpose. Then just replace that here.
And in the meantime, I'm going to rerun the profile. Oh, you're running your thing.
Yeah. So that experiment is kind of inconclusive. It seems like loading is not the bulk of the thing. So I think I'll just kill it.
Yeah, I've
Killing it might take a
kind of
little.
redirected it to VE1 just because it doesn't really matter whether it's running on one or the other.
Okay. Okay, so after that, we're doing the, I guess, key values, I'll call it key values, which takes, I'm not sure what to call it, but logits and V. Then we return logits matrix multiply V. Okay, so the idea of breaking this here is that we'll get a function for the matrix multiplies separately from everything else. So I think that would be a little bit more useful.
Yeah.
And
if you want to write, I've shared the command that I'm using to get it from the Python profiler. And I think the cumulative
okay.
time is really what we care about.
So here's an issue that can sometimes happen with AVEO, where you can try and kill, but if you're killing the process while it's waiting, it's kind of stuck.
You can
And it's like a
control
Python
Z,
thing. Yeah, but
and
if
now
you
you
control Z and then kill, I think,
%1.
-9%1, and then that will kill the thing. So yeah, that's an important debugging tip for anyone who's going to be doing a lot of vector engine stuff. But anyway, so let's run on 3. Though I am interested. You said like earlier today that the NLC Pi supports multiple VEs, so I'm kind of like wondering how. But if it does, that would be interesting. But let's look at this here on my screen.
So in the meantime, my results are there. Need to just, okay, let me share that thing.
If it's on the server, I can grab it here.
It's just the direct output here.
No.
So, right, we got the transformer block, the MHA, the attention, and then kind of for a long time, nothing. And
Mm.
this reminds me of a feature that NLCPy has. And
Oh.
there is a, like it tries to pipeline your operations so that like we are not paying as much in PCIe latency costs.
Mm. Usually a good idea.
But that also may mean that in profiling, we don't properly see where most of the time is being spent.
Mm.
Like you can see that in our pair call, and that's actually kind of interesting because in our pair call time to
Mm-hmm.
generate, we spent like 33 seconds there. And in our total time on attention, we spent 61 seconds there. And so that already is kind of most of the time that's being spent on anything at all.
Hmm. Interesting. Actually, I'm gonna do a quick sanity check with VE Progging
Sure.
to see what it says about the utilization of what we're doing. So this is a interesting, simple tool to essentially get some details of like the performance counters of the vector engine when you run it. And from there, you can see how much of your time was spent in, vector operations and how much of your time was spent in, SPU operations. And then that can help understand how much you're taking advantage or not of the vector engine. So let's give it the remaining 30 seconds it needs.
Interesting. It also kind of has its own. So NLCPy has its own ftrace built in.
That would be a little bit more useful, I think, actually.
So
10 more
that's the
seconds.
thing that I'm looking for. That is the just-in-time, or well, not the just-in-time compilation. It's the pipelining of functions.
Okay, so here's the prog.inf output. So it seems the vector time was 628 seconds of the 775, so that's usually pretty good. The average vector length is 30, which is not 256, and could
Right.
be a problem. The op ratio is 60, so that means 60% of the operations we're doing were vector operations, and 30% were SPU operations. So that's also not ideal. What this should essentially, if you're, if you want to get your money's worth out of the vector engine, this should say 256 or 255, or as close to 256 as it can get, and then this should be 99 or 100, and anything else is, missing the point. And you can also see the LLC hit element ratio is 99%. So everything is fitting in the last level cache when necessary. So that's really, really good. It means that we're not really limited per se in like running out of enough memory to hold everything. We're kind of stuck in not using the vector processing unit as much as we possibly should. So the best way to see that is with ftrace. And if you had it, could we switch to your screen so you can show how to use it?
No, I just found that in the user's guide while looking for the documentation that I was looking for. So I can share the link with you though.
And let's see, user guide, and let's look at ftrace.
It's under profiling
Where's
routines.
Okay, so ftrace region begin end. Do we have to do this for every?
Well, for every region of interest, I would probably put it around the main loop or something like that.
Can we just like start profiling, stop, and then print?
You can try it.
Yeah. Okay, so let's
those
do
are
that.
deprecated methods. You kind of want to use the ones on top.
Yeah, it's fine. Fine. Okay, so this should be used with the with statement, right? So let's see if this is useful. It might not be useful. We need to like put it around every function or something. But we can put with, and we'll see pyprov. And this was actually an MP with region. Put that in there and save. And before we return, we want to print run stats. But I guess we don't need it.
Well, it depends.
Okay, so it creates the ftrace out. Yeah, I think we don't need it. We can just do it this way. So let's try it. If I got that correctly. Oh, and the good thing about vprog-inf is that it has very low overhead compared to ftrace. Ftrace can have quite a big overhead, but prog-inf not. Does it vectorize over the string length? And can you give it a longer length? That is actually a very good point. The string length is quite short.
And another thing that might make a big difference is the size of model we're using.
Yes, we're kind of using the default, which is
the default
the
is
124 megabyte one,
I think. No, it's
oh man, I should have downloaded the big one.
Millions of parameters. So we probably want to take a look at the 1.5 billion parameters Model 2.
Damn. Okay. Yes, we do.
And another thing that, to notice is that so with those the 34 of 40 that we see, that is tokens. So as it gets longer, the longer it takes to run one iteration, the longer it takes to produce the next token.
Oh, that is interesting. Was the CPU like that?
Well, it's supposed to be like that. The longer the string is, the longer it takes to run through it. So I think that also gives us an answer to Freeman's question, whether that is whether it does vectorize or the string. It can't really, because the way that a GPT works is that it can't look forward. So it can vectorize over the entire thing, but then you add another one, and another one, another one, and as it grows, the complexity grows quadratically. And yeah.
Okay, so fortunately, I don't know how this works. I need to read more. What is this new thing? Ftrace. Use it with the if statement, with statement. And then you give it a name. But a file f is running book 13 -. So the problem is I didn't see the ftrace.out here, which I was expecting to see. So unfortunately, oh, I think I just used it wrong. And pretty sure, based off of the name, that we want it in each one of the functions. So let's do that. There's not that many. So put this here and call this GLU. Put this here and call this softmax. Then do this for the layer norm. Then the linear.
So again, Freeman. So yes, it kind of does vectorize over the history, but as the history grows, it becomes well, it is quadratic. So with every token that we add, it technically gets slower, and it also needs
and
to
you can see
redo
it
everything.
getting slower. Which also kind of makes me wonder about, like, there's some like LSTMs that are quite fast, apparently, that get very similar to GPT results. Those are always very interesting.
That's something like RKV
R,
something.
yeah, RK something something. It needs a better name. I think. But then at the same time, it's like, oh, and GPT is a better name. Be like, good point.
It's at least shorter. Like we could,
Yeah.
we have remembered like 3 letters from it.
Yeah.
Yeah, its name is RWKV minus LM. So RWKV is an RNN with transformer level LLM performance. It can be directly trained like a GPT. Supposedly, that can also be done in 150 lines.
Yeah, I kind of want to. We have time in the
It's
wall.
using Torch, so not exactly something that we can as easily bring to the vector engine.
Yeah. And I also don't think there was an LSTM implementation in there. I don't remember seeing that layer in particular, and it was one of the things they were asking us for back in the day. Okay, I think there must either be a. So usually when you want to use ftrace, you compile it with ftrace. And for NLC Pi, I'm kind of wondering how that works. But the speed is a little sus. Like, it's kind of, I'm wondering about it.
What does the documentation say about it?
Kind of says, look at the guide, which I know.
Okay.
This V offloading overhead is also included, and then for details, see that. Then if I look at this trace region, the file is generated after running your program that invokes this routine. So it was a little fast.
Yeah, to obtain performance information of all threads, it is necessary to compile C programs of the NLC Pi with NCC with the option ftrace. So you would have to rebuild the NLC Pi from scratch to really get that.
Didn't they have some like other way of doing this?
Didn't know. But in the meantime, I've looked at like I have my Python level profile back again. I've disabled the lazy evaluation, so we get some more information. And well, 99 seconds are being spent waiting for the vector engine to return on a result.
Yes, that's why we need
And
ftrace to kind of see what's going on there.
And I have also included your change with the query key and key values. And that apparently didn't take that long. Like,
Okay,
it
that's
should
good.
include the other time within here. Should it? Mostly because you see it's kind of time being spent here, and the things that should include it don't really. So it looks like when we set it up that way, that it is mostly spending time in the multi-head attention, I guess, feed-forward network, and the linear function.
Those are the big ones.
And can we do anything about that? So the linear function appears to be the main thing. And that is literally x times w plus b.
Yeah.
And yeah, feed forward function calls linear twice, and the multi-head attention also calls it multiple times. So that one line appears to be the main problem. So let me bring that up.
Actually, I kind of wonder, does
NLC
NLC Pi
model
support at?
I think it does.
It might not.
I think
But
it
let
does.
me just try it. Mat mul QKT. And then for the logics as well.
I mean, that appears to be fast enough, right? We are mostly looking at
the linear.
At linear, yeah, linear is where it's taking all the time. The plus b need to be outside.
So, rookie mistake. Okay, so yeah, that ftrace is not working out. But yeah, it doesn't seem to make a big difference. So, but linear is the big one.
Yeah.
So I guess it kind of makes sense. Freeman has a good question. What floating point type does it use? And that is a good question. I'm not sure if we constrained it anywhere in here. But the model file itself should be FP32. Let's look up is it in the utils? Yeah, I think I might want to get started downloading this. It might take a while. Yeah, so this is the loading that we do. And we, get it. So I think the TF checkpoint will be, giving us 32-bit floats back. So I'd be very surprised if it wasn't. Vector AI is offline.
It appears to work for me. Let's see.
Seems to be working for me. Let's interrupt the regular programming with a little advertisement of our terrible marketing copy. But Vector AI it seems to be working.
Is it? I remember vaguely that things without www sometimes, because the browser, if you visited it with www once, it takes care of it. I'm not entirely sure how you set that up, because I remember
it has a
that
CNAME redirect.
Yeah, I think the CNAME redirect may be not properly working. So we.
Ooh, interesting. This was also using NumPy. And so perhaps there's something that we can do there. Not sure, but I mean, it could be worth a shot. So NLC Okay, so we're doing something weird here. GPT no batch. Did you create GPT no batch or did I?
Yeah, that was me.
Oh. Okay. Oh, so that means we're not running the GPT that I was changing with stuff.
Oh,
like with the ftrace things. Yeah, that could do it. This is complaining about line 101. So in line 101, when we're doing this, okay, so this is complaining now. This was NumPy, I guess. So we're possibly not actually using Vector Engine because we were loading NumPy arrays and then doing things on NumPy arrays. But then when we did this, then it might have used an LCPy. Okay, so it is saying that only integers, slices, or ellipses, or new access none, and integer Boolean arrays are valid indices.
Can you go there? Put a list around the range.
Okay.
Well, it didn't really help.
Well, I am possibly F tracing. Possibly.
I think you're not.
Oh, that's good that that's the only real issue. And we only do it once, so I guess that's okay. Let's run this for a bit. As we now mark the 2-hour mark that we've been doing stuff, but it is very productive that we're already running things on the vector engine. But then
Yeah.
getting the max performance out of it is the main issue. And I guess we could also mess with these. Like we're giving the CPU a kind of unfair advantage because it's a small model. If we run the big model, I think that might be a different story. So let me switch this to the main thing. And tokens to generate, I think we'll do like 128 or something like that. Okay, so now we have ftrace out that we didn't have before. So that's actually pretty cool.
Oh, we did get something. Let's see
and
what happens.
Let's also look and replace the widths with would that work? I'm not sure if that will work.
Well,
Oh, that was actually probably a bad idea. That's probably a bad idea. Okay, anyway. Oh man, that's annoying. But let's look at the ftrace. CVE bin ftrace dot out. Okay, so if we look at this,
Well, that
we
gives
are
us,
seeing
as it says,
that
only for the main thread.
Should we limit it to just one core to get a better thing? But I think it wouldn't be okay anyway. Like, so if we look at the vector op ratio, we can see that these are high vector op ratios. Softmax is a low vector op ratio, which is not ideal.
It also takes
not much we can do.
Very little time, like overall.
Yeah.
We can see that within the transformer block, it's linear, which is taking the most time.
Has an 80% up ratio and but a very small average vector length. So let's running it with the big one might be interesting. Let's just run it and wait. Because it's going to take a while.
I mean,
oh man, I thought I downloaded the big one before the stream. Because it like took 30 minutes to download. But that was the small one. Damn. Okay. Well, that sucks. Okay, well, while that is downloading, I guess we can try with the original size, but with a much longer it is quite small. And when you're dealing with the vector engine, you kind of want big things. And you gotta remember to source and then run it. But actually, I kind of wonder. Okay, so if it took 1 minute and it did the ftrace, it might be a little faster without the ftrace. But yeah, it's not going to be a huge difference, I don't think.
Yeah, I think so too.
Okay, so let's see if we can run this. I might need to choose a different vector engine. Maybe I have to choose a different vector. Because while it's still just downloading, I think it is, it's grabbed a hold of one of the vector engines and kind of stuck.
Yeah, I was using the first one just now, so
Oh, well, then it must
number
mean I'm
3 is
using the third
probably
one.
the one that is. Yeah, okay, so you can use number 1 now.
Okay. So 175 seconds per iteration. And if we look at H top, CPU seems fine, right? We only have one really busy CPU, which is the expected.
Right.
Hate it how it jumps around. And
Actually, the jumping around is something that we can do something about, I guess.
hmm,
So I'm going to use B note number 1 now. Oh, you're using it. Okay.
yeah.
Wait, now you used a longer input. So it's like, yeah, I'm going to take 4 minutes now, or 5 in total, probably.
Yeah, I guess there's no point then. So the whole thing that I was kind of going for there was to see if longer input kind of made sense or not. But I guess probably not. But maybe let's switch over to your screen and I'll take a quick bathroom break, as you can
Okay.
go into
So
I don't know, some detail.
yeah. Okay. Let's see. So what I'm currently trying to do, if it lets me. So one thing that I have enabled here um, the fast math um, functionality. It didn't really do much, unfortunately. The other thing is that, as Eduardo has noticed, it's the process that is feeding the vector engine was jumping around between CPUs and different cores and so on. So I've kind of nailed it to the very first core. Honestly, it doesn't look like it's gotten any faster. So if we scroll up to the top, it ended up taking 1 minute and 52 seconds before. And the way that it's going, I mean, if we give it a few seconds to land at 1 minute here, we have an idea for how long it should take. However, this guess is actually based on the previous iterations, and as we know, it's getting longer. Yeah, Freeman, you would be surprised if it's using the vector square root. I guess that would be on in the attention line where it is, well, doing exactly that. So where it is using a square root as a reciprocal. That, I mean, we don't really see it do anything there. So it's kind of hard to tell. I mean, we don't really see it inside of of this profiler. Yeah, I guess it will be at around waypoint. And that's why I usually clear the scrollback buffer before I go back here, because there it is. So 136 instead of 152. I mean, that is faster. So just pinning the host processor to one core already makes it a little bit faster. 20 seconds would be a lot if we are comparing it to the 7 seconds that the CPU took previously. Unfortunately, we are comparing it to the almost 2 minutes that it did take before. So it's kind of, not that much of a difference. We're looking at big changes. And it looks like the linear function is being called close to 2,000 times. So that's like making that fast is going to be the thing that we want to have. Unfortunately, it is kind of using the fastest operations on the vector engine already. I mean,
In theory.
Yeah, in theory. I mean, all it does is
I'm wondering,
that.
can we? Is it possible to use the
We
VML
could do
thing?
something, the VML thing. What do you mean?
So VML has implementations for linear and functions and things of that nature
I mean, we could try
that are kind of
pulling in
tuned.
VE TensorFlow and use
Mm.
that instead of NLCPy, if that makes any
Yeah,
difference.
that's worth a shot, I think.
We could also do something entirely lunatic.
I'm all for lunacy.
So put the weights first, put X second, transpose everything, and transpose it back. Yeah, all of those transposes should take time, so it doesn't make sense for it to be any faster that way. But why not? Yeah, we got the scroll back, and nothing's happening. Are you using VE1? No,
No,
it just took a while.
just the third one. That's weirdly faster.
Yes, that is weirdly faster. If the result is actually correct, then something weird is going on. Because that was a stupid idea to begin with. It should be faster. On the other hand, I've
Well,
seen
there,
that being that way. Okay. Scroll up
yeah,
to the
like
actual output.
there is a thing about the Fortran layout being much, much faster.
Yeah, true. Now also linear is only taking 4 seconds overall.
Amazing. Amazing. Let me add that here. So you changed linear and just transposed the entire thing.
Yeah, I transposed 3 times.
So we
Can
transpose the
you
X.
can you tell Matmul that it should be transposing its inputs? Apparently.
Yeah, apparently not.
Yeah, Freeman is asking what we changed. So let's explain that again.
So
We've
the original.
transposed the things, like transposed all the things. That is something that I've seen previously make a surprisingly big difference.
And GPUs in
But
particular.
yeah. Yeah, Freeman. We can. That's why I was thinking that we might be able to tell Matmul that to transpose its inputs. Yeah, with Blast we could. No, we couldn't. Okay, so this lunacy that makes everything that's linear surprisingly faster. We have a few more places where we might want to apply that.
Yeah. I was asking what's the next thing on the trace or the profile?
Well, the next thing on the profile. So we had our linear. It took 3 seconds. Yeah, 4 cumulative seconds. We have the FFN, which takes 3 seconds, and we have 3 seconds on softmax. And we have 7 seconds on MHA. And
Split.
interesting. Create. Right. That took a while to start up, so that's why there's 11 seconds here.
Yeah. So that's another thing. We're never going to be faster than 11 seconds. So like it's going to be hard to beat the CPU if it's running in 7. It takes
But
11
we
seconds
are
for us to
looking at the
start.
7 right here, right? So that is after everything has started anyway.
Oh, okay. Is it? I guess. I'm not 100% sure how fast fire starts.
But like this should be outside of the initial loading time, because well, we didn't get any of that output before. Because the total time, as we can see, is 46 seconds here. So those 11 seconds and some other loading time were being spent outside of this loop that we are comparing it to. And so we have a list comprehension that takes 5 seconds.
Is it this one?
Yeah.
Line, what's the line? 68?
The lines don't line up with yours, because
I see.
I'm running the no batch thing, which doesn't have the ftrace regions and everything.
But if it's an MHA, I was kind of like looking at like that could be kind of slow. This try, depending on how it's implemented, could be not ideal.
Yeah, let's
So
look.
we
Let's take a
need
look
it.
at FFN for a second. What are we doing there? we are calling linear twice and GLU once.
Mm.
And well, GLU does come up, but it doesn't really take that much time. So, okay, FFN takes time because we're calling out to linear. So what does attention do? Well, that one has
That
two
has things we
matrix
can,
multiplications. So let's
is that
go
an equivalent?
more lunacy. If we put it that way,
We'll just invert the thing, yeah, and then transpose that.
here we go. Fully
And then,
lunatic. And let's see. 32 seconds is the time to beat. I should probably give it more than 1 core to work with for everything else. Oh, interesting. That actually breaks it.
mm. Mm.
But why?
We are trying to, okay, so I think the query key, so the result of query key is then square rooted with q, but we transpose the q.
Does this need to be like if we do it that way? Then
I think key was transposed
yeah,
originally.
he was originally transposed, was q times k. Interesting. Shape's not aligned. Oh, yeah. Obviously not aligned. So if
Don't we want
we
to
did
transpose? Yeah.
that way, I think we don't need to transpose it and then. Given that one of them is already transposed and the other one isn't,
Mhm.
maybe doesn't make that much of a difference. Yeah. 64, 10,
There
10.
we have 64 by 64 and 10 by 10.
Okay, let's turn it into what it used to be so we can think about the implications.
Yeah, so it was map null q t
And
and then
well, this
logits
should be
not
the
t.
same given that we've transposed everything to
Mhm.
get there.
Yeah, let's run that one, I guess.
And I'm going to give it 1 more core to work with. Yeah, that starts a lot quicker. Okay. So it fails on all the transposing. So for our key values thing, we want to be then again.
Yeah, that's the original.
Yeah. The runtime also looks more similar to what you've seen before. So that should end in about 32 total seconds. Let me clear the scroll back so we don't have to search for it. And exactly 32 seconds as before.
Let's look at
Right.
that list comprehension, I guess. I mean, it is one of the bigger ones, right? It's, I guess it's
Yeah, the
not as big
list,
as the MHA.
like it, the pair call time. I mean, MHA is calling out to other things, like right. It's calling linear, it's a split, and so on. So MHA is a catch-all in the same way that transformer block is, and their own times kind of look good enough. But attention is being called quite a lot, and I mean its per call
Yeah,
time
perform
is
attention
half as
over
much
each head.
as linear, and FFN is again coming back to linear. So given that attention is being called a lot, can we do something about that? Like, can
So
we
we are
run
splitting.
it in any way more vectorized?
Yeah, I was kind of looking at it because we we split the heads and then we zip the heads and call attention. So if our attention function was batched, then we wouldn't need to do the split. But it means that we need to create a batched causal mask,
What
which
we could
should
also
be
do
doable.
is disable this and run it without a profiler, just to see what the
Uh,
actual time is at the moment.
mm,
I mean, it is slightly faster. And so
yeah,
the thing
about
that I just
2x.
disabled is well, it allows batching on not exactly related things. And yeah, saved 5 seconds on that.
Mm. So we're getting there. Um, Causal mask, is that something that can be generated once?
Where does it come from? The causal mask.
It's in the multi-head attention. And I feel like
It
that
is using the X
is,
shape. I mean, yes, it
yeah.
could be something that's produced just once, but I don't think that we are actually spending much time on it.
Hmm. So what I'm seeing here is QKV heads. We're splitting it, and creating one causal mask, and then calling attention on each one, and then finally we stack, right? If we can get the right causal mask, we could do it without the split.
No, the causal mask is literally just the triangle
Just triangle.
mask to
Yeah.
not look into the future. It's more about putting the query's keys and values together in such a way that we get like the proper output.
Hmm.
So at the moment, we go from this to this.
X and tensions split.
You should probably also take a look at how long the CPU takes at the moment. So, did your download finish?
Nope, it's going to take another hour.
Okay. That takes a long time.
Yeah, I wish I had looked a little bit more into things. I could pre-download the file. I thought I had.
Okay. So, what can we do here? Or rather, what do we get as tools?
Plus X.
Do we get... So for now, I'm going to re-enable this. You know that it gives us 5 seconds if we have it enabled. I mean, in principle, one way of approaching that would be to create our own implementation.
Yep.
That can like produce the output at once. But honestly, that is something that probably takes a bit of time and needs some more preparation. I would prefer to find something that we can do well, now and today without additional preparation. I mean, we could also mess around and see how much effort it would be to use like the new VIDA-based things.
Yeah, I guess so. But which one do we want? VIDA PyTorch or TensorFlow?
Oh, nice. VIDA PyTorch is available on PyPy. So we don't have to build it ourselves.
That is nice. Let's see how well that works. Okay, so in here, install VIDA PyTorch. Was it on there, or was it named something else?
Oh, it's called VIDA PyTorch. Does PyTorch have something that pretends to be NumPy?
Yeah, that's what I was asking, because I'm not sure if it had it. I mean, it's kind of close, but TensorFlow did, right? TensorFlow, NumPy. Yeah, NumPy API on TensorFlow. If you put TensorFlow experimental NumPy as TMP, that works, but based on, kind of depends on how it's implemented, if it will be useful or not.
Yeah, exactly. That doesn't necessarily look like it would be.
But implementing these functions in PyTorch isn't too terrible. What was the original? I forget. What was min GPT originally implemented in? Or Nano? Nano used PyTorch. So perhaps let's try cloning PyTorch or Nano GPT and see what that's like.
So what do we actually need to do to use VIDA PyTorch?
I was also wondering the same thing. I know it exists, but I'm not 100% sure how it works.
So I guess first of all, we need to install PyTorch.
It's a dependency.
Okay, so if we got PyTorch installed, import torch.
Okay, so let me try just running this here. No, activate, and then pip install our requirements. Oh, he doesn't have requirements.
Yeah, it doesn't have requirements. You have to install things manually for that one.
Like some kind of Neanderthal. But okay, I guess I'll just set up the deployment. We can do it over in the on the server. So I'll do put it in, I guess, Nano GPT. Exclude objects, express AI, Nano GPT. I forget if it was capital or not. This probably is. Okay, so exclude the VM. Okay, and then deployment, browse another host, and I'll try to upload. I guess I have to create it first. GPT to nano underscore GPT. Okay, now I can do that. And then should be able to tools, deployment, automatic upload. There's no valid mappings, so I have to go to configuration, mappings, deployment path.
Ooh, I
Should be
think I
there.
figured out what I need to do.
Ooh, what do you need to do?
You import vida.pytorch. And then it's
And then it
available
just
as a
works.
device.
Wow, he got that far already. That's amazing.
No, I mean,
So if
I
that's the
didn't try to run
case,
NanoGPT. I was just messing around and trying to figure out what exactly, like how to use this Vida PyTorch thing.
hmm, I wish there was some example of some sort. That would be useful. But it seems that we get a 2 VE. And I remember that Nicholas added the vector engine to PyTorch, so it is should be available.
Yeah, it should be available as a device then. If you
I love
scroll
this
all
one.
the way, yeah.
Prevent Hugging Face Bert to load TensorFlow. That is such a random bug thing to have in.
Yeah, so when you import
So,
vida.pytorch, it sets a kind of monkey patches torch to have some additional things. And with that, I guess it should be possible to use the VE as a device.
okay. So we would import torch, then import Vida.
No, vida dot.
Vida dot PyTorch.
Yes.
Okay, then the device should be VE.
And I guess the data type should be float32.
Yeah. Then device type CUDA if CUDA and device else. I think we want to change that.
So
Oh,
we are
VE.
using
Nice.
Torch 1.12. I'm wondering whether, because if you scroll up a little bit,
well,
not that far, there, use PyTorch 2.0 to compile the model to be faster.
I don't think we have that one.
I mean, we can just try and see what breaks if we try to use the VE as a device.
Device type. I guess this will probably work. Actually, I could look PyTorch VE device. And let's look for GitHub so you can see what it was called. Yeah, device type is VE was there. So I'm guessing it's just called VE uppercase, and then not sure if it supports like 0, 1, 2. We'll maybe find that out pretty soon, I
It will
guess.
probably use the one that you've set up with VE node number.
Yeah. Okay, so in JPV2, we'll go to now GPT. Use 3.8 to make.
And we probably want to disable the compile functionality there.
Yeah, I set it to false, so I think that should disable it. So pip install Vita PyTorch, which depends on 1.12.1. And then transformers. So pip installed transformers. Not that short. Data sets, take token, then maybe TQDM. And then hopefully that didn't change the versions of things, which NumPy likes to do, and there's very little we can do about that.
Yeah.
Okay, and the quick start, we need to prepare the Shakespeare data.
That was fast.
Yeah, that was pretty fast. And was there?
I think you can use the I have a GPU thing because we are changing the defaults.
So this thing. Okay, so let's look at train pi then. So the train pi. So we got to import. NumPy is np torch. Import vda.torch. Right, and then
was it .torch or PyTorch?
Context.
Yeah, it's vida.pytorch.
PyTorch. Okay. And then let's see GPU stuff. Okay, so device should be VE float 32 file false.
Okay, let's.
And then we don't want torch.cuda.set device.
We want to disable DDP, I guess.
Is DDP
if you
is
scroll
that an
down,
option?
no, that is something that it is. This a DDP run? Given that we don't set a rank, I guess it will not go into that branch.
Ah, okay, so it's using distributed stuff, so I guess that would need that. And then we need to allow those things I think can be there. Okay, I guess let's give that a shot, see what happens. So readme and train. Current CUDA device does not support pfloat 16. Okay, I think we need to disable AMP.
Device, yeah.
So if
just remove the entire
else
if.
VE, there we go.
No, on context,
CUDA in device.
because it's failing on line 107.
This one?
Yeah, just comment out there.
Yeah, so we can just remove.
Just pretend that the device type is the CPU.
Yeah, that works. Okay, so no context. Device type. What is device type?
Freeman is asking whether gradient blowing up was solved by switching to remote smart differentiation. No, it was mostly solved by not coming up with architectures where it blows up.
Yeah.
So it's
and,
not
man,
like
that was...
for most people, it's not really solved as in you can't make it happen anymore. It's mostly solved in you use an architecture that doesn't have that problem in particular.
Yeah.
Line 105.
And it was...
I haven't synced it.
I'm thinking it's not uploading automatically. There we go. You know, okay. When you see the progress bar there for a second, that's when it's uploading. Okay, using slow attention. Yeah, that's a lot of weird output, but I'm not separating into TK. So model pi figure optimizers.
Does it not have?
Scalar's not used there.
It was mostly so. Freeman is asking about architectures being more implicit, or what the problem was. It was mostly that people were trying stuff out. So it was more common that you would just, throw a bunch of layers together and then throw something into it and try to see what works. And at the moment, it's I guess, yeah. people don't mess around with architectures anymore. They just take something off the shelf. It can still be a problem for researchers, obviously, but they usually know better what they're doing.
Well, maybe not know better, but like there's a bunch of standard techniques, right? So like
Yeah.
even so if you look at like Carpathy's like live stream of this, he like just instantly started reaching out for dropout and these things and stuff. So there's a lot of known ways to deal with gradient explosions, and he's grown this kind of allergy to just like doing things without any regularization anywhere. So then he just avoids it and adds regularization, sprinkles it on here and there. And that's just like experience. But way long ago, we didn't have any of those things. So it was like a big problem. You always kind of try to go 5 layers and then things isn't working. Like, ah, damn it, I have to do 4 layers, and then maybe try a little bit wider and it stops working. And like, it was very frustrating. Put like L2 regularization here and there and play around with the size to try to get it to train just a little bit longer. It's kind of very different. Like now, with all the good stuff that we have, you just like, yeah, add 15 layers. Let's add one more, and you don't really worry about it that much. Okay, so it is failing in here.
And
And
why
yeah,
is it?
not using stupid activation functions is one of those things.
Because it is removing that from
Um,
the decay list.
yes. And why are we doing it from the decay list?
I mean,
Why is this a problem?
according to the error,
Mhm.
it's like this parameter, and it's only this one. We're not separated into either decay or no decay. And there is quite a big comment on that.
Oh, in model?
Yeah. So with weight train, some warnings get generated. Subtle transformer WTE weight and LM head weight are tied, so they will appear in the no decay and the decay sets respectively after the above. In addition, because this is return duplicates, it will only return the first occurrence. So let's manually remove LM head weight from decay set. This will include this tensor into optimization via only not decayed. So how come that it is both removed and not removed?
Hmm.
So it is still in the parameters dictionary. Like is this something that would have worked if the compiler is enabled?
I wonder.
I mean, we can just...
But would it run without it? Uh,
What happened?
what happened? Not implemented error. So we can't find an implementation for estimate loss. Start arguments with arguments from BE backend. Because This operator does not exist in the backend. Yeah, I guess I
There's a
can.
lot of
Man,
that
there's a
doesn't
lot of
exist.
backends these days. Yeah, that's weird. Uh, yeah, I think we're gonna look at a lot of work tonight if we wanted to get this working on PyTorch, I think.
Yeah,
Unfortunately.
unfortunately.
Still about 45 minutes to download the big model. But what is
I mean, we could
what is the biggest bang
probably.
for the buck?
So we could try to
Say it again.
turn Pico GPT into a PyTorch thing.
Well, I have the feeling it would kind of fail. We can give it a try, though.
I mean, PyTorch has most of the things that we
Yeah,
need. They may be named differently.
mm,
Or like parameters may be named differently. Like everything that's called axis in NumPy is called dim in PyTorch.
mm.
Things like that. But in principle, we need to port GLU, softmax, lay normalization, our linear, and attention. Maybe split and stack.
Yeah, that one I'm a little worried about.
I mean, PyTorch has split.
Mm. Freeman has asked another good question. Do we have Onyx CPU runner implemented in C++? And if so, can we implement as a VE executable? And kind of sometimes it is possible to compile things. But if you just compile a thing for the VE, it's a VE executable, right? So you not only need to compile something for the VE, but then you also need to make it possible to call, do that remote procedure call into the VE. Well, that's what the Vita stuff is. It's like a VE version of CUDA. So you can implement these kernels in CUDA and then offload them to the VE. But if you're just taking some project and compiling it and kind of pretending it's a CPU, the whole thing is running on the vector engine. And a lot of the time, that's no good. That's just there's so many like non-vectorized things that it has to run, and it has to make so many kernel calls to get files and stuff like that, that it doesn't always work out so well to just compile it and run it. So like if you're looking for performance, it's probably not going to work. If you're looking to just get like a file format, like convert it, it's a once-off thing, then yeah, that actually is something that you can do. Um, and in here, but then like the other thing is, um, NCC is not really GCC, nor is it Clang. And depending on what Onyx is doing, that can cause a lot of problems. And if you're dealing with just pure C code that's not optimized for Intel or anything, not using AVX or anything like that, that works fine. But then the second you have any kind of performance shenanigans like that, it's not going to compile on the VE. So yeah, don't think it will work too well. I don't remember. Did Sam have a Onyx thing for VE? I don't think so.
Um, I I don't think so either.
Yeah. What was Sam's VE stuff? It was oh, what was it called again? What was the Sam's library called again? The JNDI one? Not
Java
JNDI.
CPP.
Java CPP. Yeah.
Yeah.
So in the Aurora branch, there is that, but was there Onyx or Onyx runtime? Yeah, I don't think he added VE support to this, so it's probably not going to work. And Onyx runtime is quite a complicated thing to build because it does have a lot of optimizations in it. It supports multiple architectures and can run on phones and stuff like that. So like just getting the C++ thing to run could take a few days.
Right.
Yeah. So I think that might be out of the question right now, but and LLVM VE is a good question. So LLVM VE does compile stuff, but it's different than the NEC C compiler in that if you're not using intrinsics, it's going to generate scalar code no matter what you do. It doesn't automatically vectorize things if you're using just the regular LLVM thing. There's this experimental backend that they have that combines the two that can do things, but I haven't used it. I'm not sure how. So when using LLVM on the VE, you have to be using VE specific code with intrinsics, and then that works just fine. But if you just take regular C code and compile it, um, it will be slow guaranteed, essentially. But there's a C++ implementation of GPT-2. That could be something to look into. Let's check that out. Darn, it's not gonna actually type the guy's username. GitHub.com GF712. Okay, so this guy, what has he implemented here? He's just loading it with Onyx and running it. So, right? Let's do the softmax. Yeah, there's nothing interesting that we could use here without implementing a whole vector engine back into Onyx, which is not a bad idea. Like having VE optimized Onyx runtime is, would be good. It's something we've kind of thought about a couple of times. But like, yeah, going down and implementing all that stuff could, it's not trivial. But is there, yeah, almost nobody implements the things from scratch. So I have the feeling we'll have to do it ourselves. A Pro Vatis wrapper. What's a Pro Vatis wrapper?
Do you think of Frovedis or something?
Frovedis. I see. Yeah, Frovedis. Frovedis doesn't have implementations of any deep learning. Yeah, it has no deep learning things inside of it, unless they added it recently, which I don't think they did. But one thing that is possible is using VML. So we could possibly create a custom C++ library in NLC that implements, one of these if these are useful. And we can do that, but is there a linear? The big ones are like linear, right? And what else? Yeah, so VML is a good question. So there is in here a TensorFlow project for the vector engine. A little old, but essentially all, this thing doesn't have that many commits. It just, there is a kernel library that was called VETF kernel. They changed it to VML, and this VML library is what implements the deep learning kernels, essentially. So if, yeah, and they've been trying to make this as fast as it could possibly be. So there's VEDNN, which implements some core DNN kernels, and pretty crazy, like linear forward and things like that. And those are wrapped by VML. So VML does require VEDNN, and it kind of presents a few, I guess, like easier to, well, the main thing is this libVETF kernel, right? So this is what the TensorFlow backend uses to like load the kernels and present them to TensorFlow and things like that. So that's what I was saying. Maybe we could use one of these if it's useful. So let's see, which ones do we have here? Yeah, so we're now on the final step, which is just playing around with it and seeing if we can make it faster. And yeah, you can see there's this op-matmul, which we might be able to use. And this is kind of how you register kernels in TensorFlow. You just say that whenever TensorFlow wants a matmul, call this function. And yeah, this is low-level stuff, right? Where you're looking, your functions need to look at what's the structures, is it NHWC or something else, NHCW, and then based off of that, call a different function. And here we have ReLU and ReLU grad, transpose. Then you have different transposes based off of the size of things. So if something's small, just do it the simple way. That's probably faster because it works all in cache. But then if it's something that's too big or 3 dimensions, then have specific implementations of that. So these are like the real low-level kernels for making things fast, and it's quite a lot sometimes. So this is the fast transpose apparently, um, all of that, and yeah, and then this is the matmul, and essentially, OMP parallel, get the num threads, and then do GEMM on those chunks. And yeah, then get those things together. So if we could call this for matmul, it might be faster, but I kind of trust that the NLC Pi team have optimized this quite a bit, but I could be wrong. And yeah, if there was some small thing that we could add and take from here, that would be kind of really nice. But I'm not sure if there is. Interesting. Okay, still have 20 minutes for the big one. So what could we do to make this faster in 20 minutes?
Yeah, what I'm currently trying is to make the Pico GPT work with PyTorch. Currently, I'm kind of stuck on converting the initial weights to PyTorch because it's a somehow nested structure of dicts and lists, where at the end there is a NumPy array.
That's annoying. I'm gonna look at the F trace again. I think that will be interesting to do while we wait. So if we take the F trace with the fast matmul, and then I'll also take do the non-batched version that you have, because I think the batched version will mess up with the F trace timings.
Yeah.
Okay, so now that and cat GPT-2 no batch, or head, I guess. And then you put this one, right?
Yeah.
Okay, so let me run this one. And VE1, I guess. What did I do wrong?
Not sure. Let's hide the banner so everyone can see what's going on there. Shapes do not align.
138, 138. Well, this linear worked fine, I think. Or did I do it wrong? Okay, so we transposed these two things and that. And this one was working fine, if I remember correctly. And then the other ones were the ones that weren't okay. But this should be the originals. So shapes 768 and 10 and 2304 are not aligned. That is a weird size. Yeah, I think we'll bring up the original and then go through it just one by one real quick. Go GPT, GPT-2. Okay, so DLU is unchanged, softmax is unchanged, layer norm is unchanged. Then linear was this one. And I guess if we delete that, then let me just check if this was the issue for reason. Could we be that lucky that we just happened to use a batch size that worked? That'd be crazy.
Batch size?
Yeah, what was your linear again? Maybe I did it wrong.
Just
Should
check
be
what
X transpose, W transpose, and then that result V transpose. Yeah, it says the shapes are not aligned. Did I change anything else? DLU linear X, yeah, then linear AC projection. Then the attention is softmax KQT square root plus mass. And then we take the softmax, the V, and we just map mode those together. Okay, and then that is good. X31, splitting shape. QV heads, and heads, and in the transformer block. I don't remember changing any of these. It's kind of weird. Transformer block. And layer 9. And it's no weird transposes there. And then inputs. Norm. That was there before. Oh, that's kind of weird. Couldn't be that. We were just like lucky and just 40 tokens worked. That would be kind of crazy. That's so weird. Why am I having problems? Well, let me compare with, so if I go to tools and browse or note host, I should be able to look at no batch. And then if we go out of this presentation mode, we have a little bit more power to compare these.
I'm getting closer.
The fast math. Is fast math important?
I have fast math enabled, like on all my runs. I think
what was it?
Fast math enabled, but I think it
Is
should.
it NLC Pi?
Yeah, you can find it in the documentation for the I think it should work that way. But it's in the NOC Pi environment variable documentation.
VENLC Pi. Fast math is default no, but this needs to be yes. Enable numpy wrap. Yeah, that makes no sense. Okay, so GPT-2's linear is this, and then this one's linear is this. Oh, yes, I forgot to reverse these. Yes, important. Okay, now we're rocking. Okay, now let's see what ftrace has to say, and if it's at all changed from the Python. Shouldn't be, but you never know.
So what exactly did you do just now?
The W and the X were in their original locations, right? So it was X times W plus B. But when we transpose, we got to reverse them, right? So I did that.
Ah.
Okay, now trace F trace dot out dot MCVE bin. Okay, so we can kind of see in order of exclusive time that GPT-2 takes the most time. Transformer block is that. Then it's mostly MHA and then linears, then attention. And the average vector op ratio, or the average vector length of transformer block is pretty high in MHA. So linear is 255.3. It's essentially good to go. I don't think we can easily make that faster. And in terms of most time taken, is there a way to optimize transformer block just a little bit?
The transformer block, I mean, it has all the time taken there because we are calling MHA.
Because of MHA.
And FFN, which again then call linear. So it's spending again kind of all its time in linear already.
We have vector op ratio is 96.
And average vector length is
And it's
long enough, I think.
2
I think it's currently attention that is really getting us.
Yeah, attention has a really low teraflop. So here we're at like 2.8 teraflops. And the vector length is that. So let's look at attention. So if we look at attention, Q shape 1 plus mask. It's weird because query key is a small amount of time. Key values is a small amount of time. So
that only leaves us with
this division. softmax. These vector lengths are pretty small too. Hmm. How much time do we have?
15 more minutes.
13. Yeah, 15 more minutes until we can try with the big boys and see if that improves our vector length. Okay, what if we break this down? So we have QK is equal to query key Q and K. Then we divide that square root is equal to QK divided by NP square root. We got shape minus 1. Then masked is QK square root plus mask. Now we return key values masked V. And then we width every single one of these. And then just kind of get that much more information. So attention QK, attention QK square root, then attention mask. Then I guess with, yeah, we have the last one because that's in there. And let's also bump this from 40 to 256 because that's a good number for vector engine in general. That slowed things down quite a bit. I guess we should also kind of, we haven't tried the 256 for the CPU, so it could be that the CPU can barely keep up. Maybe.
Yeah, maybe too. And
one thing that could, like, there's no guarantees there's not an unnecessary amount of like transfer going on as well over the PCI bus. So something that we need to
do we really
keep in
want
mind.
to wait for those 4 minutes to finish?
I kind of want to see if the tokens to generate significantly impacts the average vector length, essentially.
Okay.
If yes, then it's like a need more data, more power issue, and then if not, then it could be that it's just that the implementations are quite bad, and we can maybe gain something by implementing those in C++.
Yeah, true. Yeah, I'm mostly asking because
And
I'm trying to make this PyTorch thing work. And
oh,
it's kind of
we
failing
have no.
on a
Mhm,
same-ish issue as what we had before.
mhm.
So it again is like cannot run this A10 index tensor with arguments from the VE backend.
Yeah, I think in general there's not a lot of implemented operations, and it's kind of like we're accepting pull requests type of thing, I guess. But I do wonder, is there implementations in there, or are they somewhere else?
True. Because it's kind of I guess missing a lot if it's that way. I see
Yeah,
some implementations. There's clone and resize.
I think you could um, you could probably do a simple feed forward neural network. I'm pretty sure,
Um, let's see, it has.
which might be interesting to see, as we have softmaxes, we have reduces. Um, Cumulative sums,
Interestingly enough, it has
copies,
a value.
bitwise. Yeah, that is interesting. I wonder where it's used.
As a complex select.
Hmm,
Yes. Fill.
binary.
This has have softmax.
Yeah, but where is like linear? I don't really see it. Unless it must be implemented somewhere else, possibly.
Binary cam. Binary C.
It might be implemented in Vita tensors. That's probably why. So go here and then go to Vita tensors. Might be a separate kind of unified library where it adds more things. Yeah, this is where I think most things are at. We have transpose and all sorts of interesting things in here. They have AdaGrad implementation, and these are all running on the device with Vita, so that's pretty nice. Copy device internal.
But unfortunately, there
Let's
is
see, we
no
are
index implementation. Can we get around that, given that they have a var?
what is XYZ to H?
Funny enough, they also appear to have no um, uh, copying back to the CPU.
Yeah, you can always trust that the VE made the right calculation. You don't need your actual results. There has to be in the host side. Tensors, copy.
I mean, I'm not talking about Vita tensors. I'm talking about the
Mhm.
PyTorch.
Oh, yeah, I'm not 100% sure how production ready the Vita PyTorch things are. I'm like not haven't gotten too many updates of that, nor have I ever run it. Unlike the VE TensorFlow, that one I've
Yeah, V
run
TensorFlow is
quite often.
more there. Got way too many tabs open.
Mhm.
Let's
Okay,
see.
so we have generated, and apparently have generated nothing. A little weird. Okay, so if we look at this with the longer things, uh, attention's vector length hasn't really, I mean, it's better, um, but these are kind of weird in terms of the attention square root and QK are kind of small. Key values is 72. We're talking of the time taking most in the square root. Is that interesting that square root would take so long?
I mean, it's taking 8 seconds out of 5 minutes. That doesn't seem that long to me.
Hmm. But it's also has, wait, what are the shapes that we're talking about?
I mean, you can, like
Um,
the square root itself can be pre-computed.
mhm.
And you could do 1 over the square root as the pre-computation and then do 8 times instead of divide. I have no idea whether that may be faster.
Hmm.
Because there's like very
Could
little
be.
reason for this to be even you still should put that into the attention body though, because you're getting Q there.
Right. I was thinking of having like a global thing, and if it's none, then calculate it the first time, and then that's what I was thinking. Like a
But you're
if.
not spending time on
Um,
that. Like that isn't what it's spending time on in that region. I'm pretty sure.
hmm,
I think what it is spending time on is actually like the broadcasted division.
I see. So just like switching that out to times 1 over
Yeah,
would be slightly better. Um, the layer norm. Hmm. Could be that it's just that we're dealing with small matrices, so the vector length is unfortunately going to be very small.
yeah.
And yeah, and for that we just need a bigger model. That's the only way to make it faster. Um,
I mean, if
we
it
could make
doesn't
it
become
a
a lot
function.
slower with a bigger model, then that is already a win too.
Yeah. Um, I do kind of think that the attention is maybe something that we could implement in C. So we're doing a matrix multiply, square root, multiplying it, adding the mask, and then another matrix multiply.
Possibly, yeah.
So let's look into
I think we are not
the
going to do that
fine
today. We've
documentation.
got 15 minutes left.
Hmm. Oh, ye of little faith. Um, okay, so there was usage functions. We might want to make sure we're not using any of these non-provided ones.
Yeah, I think we're
Not
not
sure
using
if
them.
that.
I think it would complain in that case.
Okay. Okay, so where was the LC Pi? And then there was
Oh, give me a second.
the
That's something
device
to do.
management. Okay. Transfer array. I kind of wonder if there's something we couldn't do with optimizing the transfer. But this is what I wanted to see, the custom VE library. So what would that be for the attention?
Yeah, for the attention, that
So
would
let's
be more complex. Well, one thing that if you're just timing and not collecting any profiling information is, comment that out.
But I am collecting profile information.
Okay. But profiling information for the Python profiler. If you're collecting it for ftrace, then it shouldn't matter.
Oh, that makes sense. Okay, so I have this matmul. That has to be fast, right?
Yeah, I mean, that is literally
Yeah, it has to be.
the fastest operation.
The only thing we could possibly say is that maybe this isn't ideal.
I mean, what else could be there that... So I think we could implement the entire multi-head attention within one method call. And then parallelize over the heads. So that each head runs in its own, like on its own core.
That is interesting. But then we'd still need the attention as well.
Yeah, I mean, we would still need to do the entire thing, but instead of just doing the attention, it's like, let's do even more than that.
Actually, now I'm kind of curious. Of MHA, how bad are these? Each one of these steps. Would it be useful to know? Maybe. Rejection. Oops. So then let's do this. Then KQV split.
So how's the download going?
The download has a few more minutes. We're generating already. Okay, so we finished download and now we're generating. Seems to be quite the hunky model right now, but we are
20
running
seconds
without a
per
lot of stuff. token.
Yeah, per
So
token.
take
That is, and
41
it's
minutes.
becoming more and more. I guess we don't want to let it finish with
Yeah.
the way it is.
I think maybe we want to look into. Okay, first let me finish this just to see if there's something stupid in one of these, I think. And I'm interested in seeing if, like, strangely try or something like that is super slow or not. Then we have our attention, but so we have one attention, but this is calling it multiple times, so that gives us the time. Then we can see the H stack time, then the final projection time. Projection, merge heads. All right. Okay, and then we have KQV heads attention. Then we have causal mask generation. KQV projection, KQV split. These are both being the same. This is KQV heads split. Yeah. KQV split, and then this is heads split. So we split the different heads. Then do that. Okay, let's look at this code here.
Yeah, wait a second.
Hmm?
I've started it with the big model for 40 chunks, for 40 things on node 3.
Mhm.
And I mean, at 4.3 seconds per iteration, it is, well, at least not 20 seconds per iteration as what it was before.
Yeah.
And for you, it's running currently on with the small size.
Yeah, I'm running it on small size. Yeah. 124.
And okay, it's getting slower apparently. Guess it's at 4.7 seconds per iteration.
Okay, cool. So we have a lot more fun things now. So we
could try it on
of this time.
I mean, that's also
The big thing?
without. Yeah, I mean, it's running without a task set, so it's jumping back and forth. Let me give it infinity.
Okay, so transform block is 13 seconds. 7 is linear with perfect vector length. MHA FFN has a perfect vector length, so probably nothing there. The head's attention and the attention have bad vector length. Kind of show up on the top. Then the square root is 113. The layer norms that, but they're like insignificant amount of time. So the time to generate was 39 seconds. And of the 39 seconds, if we made any major difference, it would like save 3 seconds with this KQB head's attention. Or totally optimizing MHA significantly. That would get rid of a significant amount of linear calls, though. I'm not sure if that, like a little bit of fusion happening could be useful.
I mean, in principle, it shouldn't be moving stuff back and forth. So what we get is just calls to the device with pointers going there.
Mm-hmm.
Mm.
Well, one thing that's kind of, I guess, kind of interesting is the megaflops is stuck at 3, essentially. We're like stuck at 3 teraflops or
I
gigaflops.
guess we should try it on VE node number 3 to see whether we will get more.
Mm,
Just wait a second, like 8
okay.
seconds. Also, we probably want to see how long the CPU takes on that model.
Mm. Yeah, we should.
Because
Let me
we
grab
got,
the original.
like, it finished with an average of 6.3 seconds per iteration and 4 minutes
Which
12.
seems pretty decent. Okay, so let's go and create a new file, GPT-2 original. Okay. And let me try running it.
We want to give it its best performing ability. Then do the task set.
Okay, so
You can set the
the
model size
size
on
that
the
we
command
want.
line. Yeah, that is back
Ooh, how do you do that?
Yeah, task set. Yeah. It's minus model underscore size.
That's the one I want, original.
Yeah.
It's going to take 1 minute or so.
Let's see
For
how
40
it will
tokens.
end up, because it becomes slower and slower as it gets more tokens.
I see.
But I mean, that still is slower than. I mean, that's still faster than what we got from the vector engine at the moment.
There's one quite significant slowdown there, but a minute and probably a minute and a half, I guess. Maybe 20 seconds.
Another interesting thing will be to see just how long it takes. Not how long it takes, whether the output is actually the same.
I guess it should be. It's not exactly
it is the same
same.
as on the vector engine.
Oh, it is this. Okay, then yeah, then that's good. A minute and 30. Okay.
A minute
Actually,
30 with 2.2 seconds per iteration. The vector engine ended with 6.3 seconds per iteration and 4 minutes 12.
I wonder if Koopy works. Let's give it a shot.
Let's see.
And kind of see the vector engine get completely destroyed by.
Yeah, if it doesn't
Why can
work, you
it not
could
install it?
also yeah.
Let me see if I can get a wheel for Koopy. No, I can't.
Yeah, try installing Jax.
Okay. Install Jax. Okay, and then what was it in the blog post again?
Import jax.numpy as np.
Okay. And then trying that, but with GPU. Requires Jax lib to be installed. I see. So first, yeah, we probably should upgrade pip to the latest, and then we want the CUDA one.
I mean, we can also try the CPU one just to see it being extra destroyed.
Wait, then how do we set which backend it's going to use?
No idea.
Well, I
Let's
mean, I'm
check
sure it's going to be
documentation.
destroyed totally by the CUDA backend.
Yeah.
It's going to be like ridiculous. Okay, so now run this. Now we see the full power of this fully functional and operation battle station, maybe?
I mean, it is using 61 gigabytes of GPU memory.
That's a lot. That's a lot of memory. What? That is a lot of memory.
And also,
It's more memory than we have on the vector engine.
yeah.
That could be a thing. We just need to wait for the thing to kind of initialize, I think. It's probably going to do this like only the first time. Remember how we had this problem a lot in V4J? Like,
Oh, yeah.
I think.
You could have installed a specific CUDA version, I think.
Running CUDA 8.6 and CUDA 11, which I think is the right one. Yeah, it's running now.
Yeah. Okay, so
but if it's running,
for the
if it's going
first
to run like this,
iteration,
then
if it's running
yeah,
like
it
that,
should be
then
pretty slow. Yeah, if it's running like that, it was like, holy shit, look at how fast the vector engine is, you know.
exactly.
What is this thing doing? It's sitting at idle, but sure it's taking its time. Is Jax not a good idea, possibly?
We should probably
That might be the
put
case.
I mean, in the blog post for that, he essentially says just use Jax. But I mean, we could also try it with a smaller model first, just to see whether it's something about the model being big.
But we have 80 gigabytes of memory.
Yeah, I know.
Even if it's using 61, which... So I guess you can say that we totally kicked the ass of the A100 with the with the VE right now. Let's ignore. Let's put the CPU
Yeah.
to the wayside for a sec.
I mean, even if it is a batch size thing, it shouldn't take a minute for one token.
Yeah,
Um,
that's what I would. That's kind of like what I was expecting the CPU to take in
but
general.
what you can do,
Um,
just for fun,
mhm.
is when calling the GPT-2 method, or let me check. To we are calling in generate. So we could try to apply some just-in-time compilation here.
Mm. Yeah, I was looking to see if there was a thing for that. I think we kind of have to. That's probably like compiling it every time we call. Um, so do we want to
Yeah, I'm going to do that.
Jax?
Give me a second.
Okay.
From Jax in JIT. I think I can put that as an say decorator there. Um, can I think I can.
Yes. Yeah, you should be able to. So
Okay, so
be
there
like
is a
from
new file called GPT-2 GPU JIT.
okay.
So you can
We
call that
grab it.
instead.
If I synchronizes it, do it both ways. I think it does. Okay, so let's look at.
And you also don't need the tasks that set in that
Yeah, I guess we
case.
don't.
And it's GPU underscore JIT.
Oh. Um,
Yeah, that is,
okay,
I
so
guess, one of the limitations then. Scroll up. More. More. Here, where it's using range, turn that into a list. No, it
right.
it still
It's
needs
Python.
to have the range there. But you
Oh,
need to put list around that too.
so same deal as
Yeah,
NLC
in
Pi.
principle, the same deal as with NLC Pi.
And then has
Okay, put tuple instead of list there. I mean, if it necessarily wants a tuple, can get that. Okay. Let me
use
put JIT
array
on.
or arrays. But what is it
Okay,
saying? It's saying
let it run again.
R.
I've put the JIT on something where it's going to spend more time, or like where it spends most time, but doesn't do that kind of thing.
Let's put it back to the list.
Yeah.
But then where's the JIT now? Because I think I'll override it.
Yeah, I put it on transformer block.
Okay.
Okay, let's
GPU
put
programming
it on
sucks.
attention and on linear.
Okay. So tension and linear. Those are the main ones.
Yeah.
No, I kind of wonder if it would work in MHA.
Probably not. Like he's using a lot of parameter unpacking there.
Mm-hmm.
So Freeman is asking whether the ultra slow run, whether the CPU usage suggests that it was compiling a lot. It actually did not. And
yeah, but even if you do look, when it is running like a GPU compiling thing, if I remember correctly, it was like single threaded, so there'd just be like one
yeah,
CPU kind of really
but
trying, and you could have
it's
like
not even
80
that.
cores. Yeah, it's like not doing all that much. So weird. At this point, it's like, oh wow, the vector engine is the nicer thing to deal with, and
Yeah,
so
kind of
much faster.
surprising.
Yeah, that is quite surprising. My expectation was that it would do all 40 in a few seconds.
Let me
Why?
check with the small model. In
Okay.
the small model, it runs with like 1 second per iteration, so it ends at around I guess 40 seconds. That's actually,
With the small model,
yeah. So I'm running it in parallel. I mean,
even though I'm still,
yeah. I
I
mean,
guess
you can
it
use
is like
multiple
totally
processes
idle.
can use the GPU.
Yeah. So I just get rid of that. Just a gigabyte. I don't know. It
Yeah,
just
it's
always
done.
wants to use 61 gigabytes, I guess.
No, it's just done. Like mine is done now
Oh,
with a small model. And yeah, 45 seconds. So at 27 seconds, the VE was actually faster, and the CPU probably would smoke all
oh.
of this.
That's an interesting result.
I mean,
But
it makes
why is it not
sense.
running for me?
It's just, I guess, takes a very long time the way that it is set up in this tiny example GPT.
Hmm.
I mean, it did get faster. I mean, it went from a minute per iteration to 22 seconds per iteration.
Hmm.
Let's watch the
That is
GPU
weird.
utilization,
And
because it feels like it's mostly spending time off the GPU. The GPU sits essentially idle, goes to 2%.
yeah,
Do a watch N1.
yeah.
You can see how the utilization just, it's
Hmm.
like, yeah, a bit, nothing, 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 nothing. And it's like a blip. And so the GPU does nothing
Hmm.
most of the time.
That's interesting. Huh. Well, I think that will take a while to figure out. I mean, in the blog post, it was like, yeah, running on GPU's homework, and he didn't say that this was necessarily the most optimized thing.
Yeah.
But I do kind of wonder about Koopy. Like, why can I not install Koopy? Okay, let's see. Getting started, Koopy. Python 3.8. I have Python 3.8. And I can have those. Maybe I have to do one of these. So which one? What were we on
So
again? 11.8. So 11.2 to 11.8, we want to install this thing. Apparently. I'm not going to wait for this. It's too slow. Okay. So pip install Koopy 8.
you probably could, like on the JAX side of things, by replacing the
Mhm.
list comprehensions with a VMap. And then instead of doing the split, getting, there would be possibilities to improve things.
Mhm.
But on the other hand, we don't actually care all that much about anyone in particular.
Mhm. Although I kind of wonder if that would be useful. Unsupported type ND array. What are you talking about? How can you call yourself Koopy if you don't support ND array?
Yeah. Go to the utils method, utils
Mhm.
thing. Scroll up all the way.
Ah,
Yeah, I mean that wasn't NLCpy for the longest time because I've
yeah.
changed that.
Oh, see. But then what is the...
Yeah, I mean that was NumPy all the time. I think you should change that to CuPy there
Yeah, but it
because
didn't change the... It didn't really change anything. So if you do that, it still says that can't support those things. And it's here.
yeah, it's when it does. Hmm. So you could try to turn everything into CuPy array. Um,
Down here when it loads it.
yeah, kind of. So there is. I'll just drop you that function, which I used on my unsuccessful PyTorch tests just now to convert the parameters to, well, whatever it needs to be. So you could try to use that and use CuPy.sRay with the parameters that you get from loading.
Convert to torch. So we start from there. Okay, so this, so convert to CuPy. To And then otherwise,
Well, it's NP in this case, as array. No, you don't need to do
and
the last part. Okay.
I
Now
see.
you can apply that to the parameters
Each one.
and params.
This one.
Yeah. No, not h params. Params.
Oh,
And I think that should be enough. Oh, it's all one thing indented. Oh no, that looks fine. It was just the def.
yeah.
Didn't fail yet.
Interesting.
Yeah, that's more like it.
There we go. That's more like it. That's definitely more like it. And
okay,
then
let's try the
that's what
big
I'm
model
expecting.
size.
Thank God. And I was about to say, man, I wasted $20,000. I can't even run GPT-2. Shit.
Takes some time to get going, I guess, but yeah, 2 iterations per second, not 2 seconds per iteration.
Hmm.
And yeah, it still uses just 24% of the GPU.
Yeah, interesting. It is, I guess, surprisingly slow given how fast like GPT-3 is. And I kind of wonder, is like, oh man, how many GPUs are we going to need to like have a real
Can you
chatbot?
run it again? Maybe for a bit longer. Like, what was the parameter?
What was it?
Yeah, n tokens to
N
generate.
tokens to generate. Let's do
Yeah,
256.
is good. Okay, so it starts up. And we are using 7 gigabytes of memory, 8 gigabytes of memory, and we see about 24% of utilization.
Hmm.
So it could be 4 times faster still.
I think we'll probably need batching for that though.
Batching what?
Like multiple prompts together.
And then like per prompt it isn't that faster, that much faster. It's just that, I mean, the latency per prompt is the same. It just, the throughput is higher.
Yeah. Yeah, that's what I'm saying. I think it should be possible to get more throughput by batching things. This is my
Yeah,
guess.
so now we are at 9.6, 9.7, 9.8, 9.10 gigabytes of usage, and the utilization is actually rising as it gets longer.
Mm.
I mean, it makes sense. It's working on more data at once.
Yeah. But man, it just kind of goes to show like how much raw horsepower is in OpenGPT. Or I guess I think it's possible that we can get double the performance by using FP16. We
And
are in
setting things up
FP32 mode, I think.
correctly and everything. Also interesting how it just gets stuck in the loop.
Unfortunately, we are dealing with GPT-2 after all.
Yeah. Okay, I think it's kind of time
Mm,
to finish
Paper.
this up. It's almost 2:30 in the morning for you.
Yeah. So yeah, that was a fun kind of stream where we were able to get something up and running fairly quickly with the vector engine. Um, and while it wasn't super fast, um, it did work, like out of the box, which is nice. Um, and we were able to show how to debug things and like profile stuff. But then, yeah, the hard part is unfortunately the hard part to go in and optimize and merge the kernels and things like that is probably where um, it's like that's probably the thing you have to do to really get a lot of performance out of it. And that's going to be quite difficult implementing all that in C++. So it might be something that we do in the next stream to just like take attention and make it fast on the vector engine. Um, but yeah, it's also interesting to see the how kind of non-trivial it was to get it running on the GPU, and even on the GPU, it wasn't super fast. Um,
I mean,
so
given that
yeah,
all we did was just install CuPy, that is
yeah,
pretty good. Um, but yeah, I mean, we start with an implementation that actually says in the README that it is super slow.
yeah, yeah. Like not having a compile is probably not ideal for performance. So yeah, doing things with NumPy can be, you know, interesting for like learning stuff and doing stuff, but then like actually implementing things is like an extra challenge on top of that. Um, so yeah, so I think we'll end this stream here at 2:30, and I think we'll see everyone else again next week, same time. And yeah, I think we'll make things not be so low level next time. There was never
Yeah.
that many people watching, so I think it was kind of went way over everyone's heads. So yeah, I think we'll see everyone next week.
Yeah. See you then. Bye bye.
Okay, bye.